Sì, vado in italiano, no? No. Signore e signori, buongiorno, benvenuti.
Good morning, ladies and gentlemen. Welcome to Vicenza Oro 2022. It's an extraordinary edition because we had to postpone the January edition. Welcome on behalf of Italian Exhibition Group. This is the fourth day. Tomorrow we will close the trade fair. So we are approaching the end. I'd like to thank Legor and Mr. Poliero for the long-standing collaboration with IEG on the scientific and cultural issues which are part of the driving engine of the fair. In the past 2 years, the trade fair did not close. We continue to organize events with the technology industry, and Legor is the most important representative for that. And I think that we should praise them for the beautiful outcome we have achieved. So we have to congratulate the trade fair, the exhibitors, and the partners. In the future, we will continue to invest on JTF. This is official. We will continue with the event. I'd like to ask my colleague, Matteo Fassura, who can expand on the statistics of T-Gold so that you can appreciate the growth of the sector. Thank you very much. T-Gold is part of the offering of Vicenza Oro, more than 140 companies. The large majority are Italian. The second present country is Germany. In the pavilions, we see a lot of creativity, and the engine of that creativity is technology innovation. That can be seen in the framework of T-Gold. As for the future, we are trying to have a more detailed mapping of the supply so that buyers can identify their potential suppliers. At the same time, we would like to tell the audience what companies can do every year and what they exhibit in their booths. The idea is to convey the right messages to the whole industry, which has real attention to technology innovation. Thank you very much and enjoy your event. Good morning. I am Massimo Poliero, President of Legor. I'd like to thank you on behalf of the company, the collaborators, and the scientific committee. At last, we are here, present after 2 difficult years. Today, as compared with the past, we have many people connected through the screening. So we are thinking about the format we will use in the future. The possibility to have people online offers many more opportunities for those who are linked. I'd like to thank IEG in the presence of Canello and Farsura for their support and for the collaboration that we have carried out in the at least past 10 years. Jewellery Technology Forum was held for the first time in 2004. This is the 17th edition, so we have a long history in the field of technology. We know that we have been pioneers of innovation and technology. We want to support the companies, the entrepreneurs, the engineers, production people, craftsmen, the research sector, in university institutes, to have a platform, to have a dialogue. This has been a driving engine to organize this forum. And indeed, its natural place is T Gold. We want to push even more. We'd like to improve the landscape of international speakers. This is our wish. We want to further develop this industry. We want to continue with the synergy that we have to give our contribution to the growth in the industry. Italy is at the center of the technology sector. There are many companies present at the T Gold exhibition. We will continue to push so that this event is a place for discussion on research, technology, and innovation, and to have ideas for the future. I'd like to thank two persons in particular. One is connected, who is Chris Colty, who has been with us right from the start in 2004, and the founder of Santa Fe Symposium, Eddie Bell. We will meet him next May in the closing edition of Santa Fe Symposium in Albuquerque, and started many years ago. It's at the 32nd edition. So thanks to them for the contribution, the support they gave and are giving to JTF. The floor to Elio Palma, who is the moderator. In the afternoon, we'll have Andrea Frieser, and let's get started. Thank you very much. Good morning, everyone. Thank you very much for being here. As Massimo said, this is the 17th edition. I'm proud to have been a member of the scientific committees for years. I will continue to do that. It's an honor to open this symposium. We have a number of very interesting papers grouped in three parts. Some concern economics, thanks to the support of the Intesa San Paolo Bank Research Institute, then a part on technology, metallurgy, and then 3D. According to the agenda, the morning session will close at 1 o'clock, and then we'll have questions and answers. I'd like to introduce the first speaker, Mrs. Daniela Corsini, who is connected remotely. Good morning. Good morning, everyone. She got a cum laude degree in statistical economics and social sciences at the Bocconi University. She started in 2006 in Luxembourg. As a portfolio manager, she's in charge of equity funds in emerging markets. In 2011, she became a member of the Research Institute of the Intesa San Paolo Bank, managing the commodity markets, energy, agriculture, industry, and precious metals. Since 2011, she is a member of the CFA Institute. She is going to speak about a very topical subject. She speaks about the transition to a post-pandemic world, so really a burning issue. Thank you very much. You have the floor. Thank you very much for what you did, and all the participants devoting your time. I have some slides. I hope I can share the screen. Otherwise, I ask the engineers. I'm sorry, the screen sharing does not work. Anyway, during the pandemic, we had an unprecedented shock in the world market of raw materials, and gold in particular. The demand for gold in 2020 dropped by 16%, with a dramatic drop for the demand for jewels.
di oro da parte delle banche centrali, proprio perché le banche centrali
central banks had temporarily set aside the objective of diversifying resources and concentrated their resources in the monetary policy to expand and support the economy affected by the pandemic. The only gold demand which dramatically increased was in the financial sector. There was an increase in ingots and coins and ETFs, so financial funds based on gold. This contribution to the world demand doubled during that year and was 24% of the total demand for gold, which indeed had a major impact. In 2021, thanks to the announcement of new vaccines, thanks to the economic recovery, the world gold demand normalized. This has not yet been accomplished, but still there was a 52% increase in jewels demand at world level, plus 93% in India and 83% in China, the countries more affected by the pandemic and by the lockdown measures to contain contaminations. Technology demand was plus 9% and demand of central banks plus 82%. Opposed to this very robust growth, the financial demand of ETFs dropped. And ETF's contribution was minus 4% of world demand, as opposed to the 24% of the previous year. As for the price of gold, the volumes of gold in the hands of ETFs, the correlation is very good and significant. Quotations increased in line with the accumulation of gold by ETFs. This correlation dates back long ago. Already in 2019, with very expansive monetary policy, there was a first increase in gold, guided by the accumulation in ETFs. This push for the demand of shelter goods continued in 2020 and stabilized between 2020 and 21 when it began to drop. With the war of Ukraine, the demand for shelter goods or safe havens continued to be key. That indeed brought to an accumulation of ETFs who bought more gold than in the past, because the financial market was asking for safe goods, and the quotations of gold followed suit. The financial demand will be the main driver for gold quotation also this year. As I told you, the normalization process is nearly accomplished in terms of volumes consumed in jewelry. We are back to the before COVID. In some cases, demand is higher than the pre-COVID time. The real driver will be the financial markets will make the difference. The main topics will be connected to war and inflation. In the first months of this year, gold quotations increase was accompanied by fear of risk. The correlation was very significant, with a fear of risk and price of gold. And volatility in the financial market jumped. In 2022, there has been a major increase in the price of gold, followed by an increased volatility in financial markets. On the contrary, other traditional drivers of financial demand for gold, such as American dollar or more restrictive monetary policies, are no longer so important. This is so, but for the demand for safeguards was the main driver. The American dollar is considered a shelter, so when panic is there, gold dollar went up, which happened in these first months. In conditions of less tensions, the correlation between the two is negative. So when the dollar goes up, usually the gold goes down. This has not happened, and it might not happen in the coming months, notwithstanding the increase in the dollar. For today, the main issue is the search for protection. As for the yields on interest rates, mainly in the US, there was an increase, and the Federal Reserve Bank this year announced a first increase in the interest rates, which probably will start the trend upward of the American monetary policy, which is explained by the willingness to contain and avoid overheating the economy. Usually gold at the beginning of a restriction cycles, its value goes down. This has not happened. So we think that the increased interest rates will have a lower impact as compared with the past, because there are more geopolitical concerns and the inflation will remain a problem. We don't think that central banks will increase rates so much to damage the value of gold. Real rates will remain negative for a long time, even though nominal rates will continue to grow. And for that reason, gold will continue to be supported by monetary policies, notwithstanding this restrictive approach by the Federal Bank. As for price forecasts, gold is vulnerable to high prices. It might be beyond $2,200 per ounce in the event geopolitics gets worse, especially in Ukraine, and then in the following quarter might range between 2,000 to 1,090. Average price for 2023, $950 per ounce. Silver will follow. The correlation with gold is very strong, even though the fundamentals of silver are stronger, thanks to the possibility to use talco in the future with an overperformance of silver in the long term. That will not be the case in the short term, so we hope to remain between $22 to $30 per ounce. In 2023, $25 will be the average price in line with the present market. Metal, platinum and palladium prices are different. The demand from the automotive sector is the key issue, together with geopolitical risks, in particular for palladium, which is produced in Russia by 40% of the mine production in the world. Second producer is South Africa, 40%. 85% then, the world demand for palladium comes from the automotive sector, so quotations will continue to fluctuate depending on the concerns for Russia or recovery for the automotive sector, which is now limited by the lack of chips. And probably for this metal, we foresee between 2,500 and 3,200, and the average $2,650 per ounce. Platinum, considering it that Russia is less exposed and automotive is not really relevant in this demand, it is 20% of world demand. Jewelry has a weight, 15% of world demand, and for investment, 9% in 2020. So platinum will be more correlated with gold in the coming months. We do expect between $950, $1,350 per ounce, an average of $1,200 ounce for 2023. The floor to the colleagues of the Research Institute. Thank you.
Grazie,
Many thanks, Mrs. Corsini. And now the second speaker in the economic area, Mrs. Sara Giusti. The global scenario of the gold industry during COVID-19. Mrs. Giusti is graduated at the Varese University and economist at the Study and Research Academy of Intesa San Paolo. She focuses on industrial policies, in particular fashion and the districts of Tuscany and Umbria.
Grazie, buongiorno.
Thank you. Good morning. In my presentation, I will have a first part where I will present the results of the gold industry in 2021. And the second part will focus on the current competition framework and the challenges which are emerging. So let's have a look at what happened in 2021. Despite the fact that in 2020 the jewel sector was one of the most hit sectors because of the lockdown, in 2021 there was a rebound in terms of turnover, which made it possible to recover the pre-crisis values and even overcome them. And this was very significant, even greater than in the manufacturing industry and even better than the fashion industry, which has not yet filled the gap generated in 2020. These are the value results, but you see also the trend in terms of quantities is very favorable. So the sector actually was able to recover that rebound of the world demand. In 2021, the world demand of gold jewels went back to 1919 values, and it was more than 2,000 tons. And in the right picture, we see the subdivision into the various markets. So a major contribution was given by the Indian market, which practically doubled demand. And this thanks to a good recovery of the economy, a release in the restriction measures, which caused a new trust, and there was an increase in the number of marriages. So even though there were still restrictions in terms of number of participants, nevertheless, gold jewels were bought for marriage events. Well, in China, we have a 6% growth as compared to 1919. Certainly, there was a greater demand due to the economic recovery. And we noted a shift towards design objects as a reaction to the needs and requirements of younger generations. Well, also in America, we have a good recovery. And the demand for jewels probably was able to increase despite the fact that there was also a very slight increase in journeys and tourism. So this explains the situation that we see described here. So a significant growth of exports In 2021, exports were equal to 6.6 billion euros. And again, here, based on ISTAT, we had an increase in terms of values and also in terms of quantity. And this took place in all the main markets. We see a good consolidation of the US with more than 1 billion euros. The US is the first market for our exports, thanks to the progress shift towards high-range products. The same applies to Turkey and the Arab Emirates, which is the second country. You see that they recovered the sales in terms of values, but not in terms of quantity. And if we look at the three main hubs that together represent 70% of exports, well, we can note that all in all, the sum of the three districts, Arezzo, Valenza, and Vicenza, could go beyond the values of 2019. So it's important to consider also the distribution and logistic policies carried out by the main luxury companies. For example, if we look at exports towards Ireland, well, that is explained by the role that this country has in fiscal terms and also in logistic terms. So this is the way in which we can analyze these flows. And then another aspect which is very important at a territorial level is that we are commenting these stats in terms of values. And there may be a sub-estimation of the recovery in Valenza, for example. So this is to explain the major recovery of the sector. And now it is necessary to look at the current competitive situation. Now, if we had presented this survey in January, probably we would have talked about an economic recovery which was at very high levels. But unfortunately, the war in Ukraine has added extra tensions, which go and worsen the situation that we inherited from the pandemic. So here you see the main channels and the main effects. So the first channel is certainly international trade. And of course, sanctions against Russia have caused a stop in the exports. And then the issue of traffic. Think of the Black Sea routes where there are many ships which are stopped there, and many shipping companies which have decided not to work in Russia because it is too expensive and too risky. And then the second channel is the financial one, bank crisis, company crisis, and then the other two aspects, which are the ones which are of greater importance for the gold sector. Certainly the issue of the prices of raw materials, with an increase in prices and uncertainties in terms of sourcing of gas and oil, and then the price of precious metals and the difficult sourcing. And then another issue has to do with uncertainties, which have to do with investments, which have to do with planning of investments, but also uncertainties in terms of consumption. There is a fall in the buying power of families, and this will reduce consumption. Now, In terms of the impact on Russia, well, sanctions caused an immediate devaluation of the ruble, and sanctions, because of sanctions, the Russian banks could not support the currency, and so there are many uncertainties. There are forecasts which estimate a double-digit GDP fall. So there is still a very high tension. Now, if we move from Russia to other countries, well, we can say that this crisis will have an impact on Europe, because European countries have strong links with Russia, and by means of international trade, we will have an effect also on the trade balance, and then there will be an impact on propensity to saving. And unlike what happened during the previous crisis, this propensity to saving will fall. So, and this will have an impact also on inflation. Here we see a representation of the forecasts and how they have been modified after the 24th of February. So watershed date in terms of forecasts. So we see that there is an increase in inflation, both in terms of general inflation and core inflation, due to the cost of energy. But here we have another important comment to make. It's true that we have a higher inflation, but it's appropriate to say that as these are shelter assets, an increase in uncertainties and inflation could partly promote more demand. And then another channel of propagation of these tensions is due to the crisis of mobility, of logistics. On the left, you see the Italian exports towards Russia. And we see that exports towards Russia already decreased after 2014. Currently, the Russian exports is about 5%, and also the tourist factor has fallen, although it is a type of customers and clients who can spend a lot of money. Now, going into greater detail, we focused on exports. Again, we see that exports to Russia do not have a particularly high importance, from 5 to 0.5. So these are direct exports. So perhaps they can be underestimated, because we're speaking about a sector where not always sales are carried out by direct logistic means, but there can be intermediate hubs. So it's data that we have to interpret, so to speak. And this applies also to district specialization. We see that the 3 Italian districts specialized in jewelry, direct sales to Russia do not have such a big importance. And then finally, we would like to give an original view of the situation based on some figures that we analyzed together with the industry. These data were published a few days ago, and the members of the Jewelers Club were asked what would be the effects of the current crisis on sales. well, the impact is particularly negative. There is also a question of size because smaller companies, of course, will have a greater impact. But it's interesting to note on the right what are the sectors which are most hit. So first of all, the prices of raw materials and also the issue of transport and logistics, and then the lack of raw materials. And then there is another issue which is typical of this sector, which is the reaction capacity. So 70% of the sample answered that they are revising the organization of their companies in terms of price policies, but also in terms of structural projects related to sourcing methods and marketing channels. And then we would like to close with this summary. This is a result of an investigation that we have had carried out in January, where we asked the members of the club what were the most important means in order to react. So first, we have training and education of human capital. And then second, digitalization and research and development. So there are two aspects that we should highlight. Training and innovation are certainly sectors that companies want to develop, and they are not alternative in nature. So for them to work, we need to have a synergy between the two areas. Thank you. Thank you.
Thank you very much, Mrs. Giusti, for this very interesting description of the landscape of the industry. Let's move to the metallurgy session. We have a very distinguished speaker who has been with us since the beginning. Hi, Chris. He will speak about the evolution of platinum jewellery alloys from the 1920s to the 2020s. He is a very distinguished speaker on the technical issues at the Santa Fe and JTF symposia. He has more than 40 years of experience in the jewelry sector and in the World Gold Council before establishing his company in 2009, a PhD in metallurgy from the Surrey University. Before working on precious metals, he worked in the energy sector in the UK and Switzerland. He will speak about the evolution of platinum alloys in the 20th century, which was necessary thanks to the technology and metallurgy challenges to develop and improve jewellery alloys. Please, you have the floor.
Good morning. I'm going to share my screen. Just wait a moment. We all associate the early use of platinum in jewellery with the 1920s. About 100 years ago. Since then, it faded, and then the market really grew from the 1970s. And there has been much technological change. In particular, there has been a significant development of platinum jewellery alloys, and my presentation today reviews these changes. As I shall demonstrate, there has been a considerable development over the last 25 years. So let us begin with a quick review of the history of platinum. Platinum has only been known to Europe since the 16th century, with rumours of the existence of a white metal, platina, in Central and South America. Alloyed with the other 5 platinum group metals: palladium, rhodium, ruthenium, osmium, and iridium. And these were exploited by the pre-Columbian Indians of Ecuador and Colombia in northwest South America. Analysis of ancient trinkets indicates that iron and copper were also present as impurities. We note that it's since become used as a jewellery metal in Europe since the late 19th century, and that many jewellery alloys are based on industrial alloys. Its acceptance as a hallmarkable jewellery metal in the UK came much later in 1975. From this time, with its now much wider availability, platinum was promoted by the platinum producers as a rare, high-value jewellery metal, and platinum jewellery grew in popularity, mainly at 950 and 900 finest qualities, in Japan, in Europe, and the USA. Although some growth in demand began earlier in Japan in the 1960s for historical reasons linked to the ban on the import of gold until 1973. Platinum Guild International was formed in 1975 to promote the use of platinum in jewellery. This marketing and growth led to some alloy development, such as the platinum cobalt alloy for investment casting, and the use of gallium additions to produce heat-treatable alloys with higher strength and hardness. Initially, only a few alloys on the market were on the market to meet manufacturing demands, and these were classified as casting alloys, general purpose alloys, and hard alloys. Huckle of Johnson Matthey reported on the development of platinum alloys to overcome production problems at the 1996 Santa Fe Symposium. He noted that platinum and its alloys had some different characteristics compared to gold and silver, notably its weight, hardness, and thermal conductivity, and that its alloys have a high density as well as very high melting points. Its high surface resistance leads to clogging or galling and high wear of saw blades, files, and machine tools. He notes that in Japan, platinum palladium alloys are in common use, particularly platinum 10% palladium alloy, whereas in Europe, platinum 5% copper is preferred. Applications, platinum 5% cobalt is finding success. In the USA, he notes platinum 10% iridium is commonly in use as an all-purpose alloy, and that platinum 5% ruthenium is used where a hard, good machining alloy is needed. He also notes platinum 5% cobalt alloy is finding growing use for casting applications in the USA. Metz of Platinum Guild International also reviewed platinum alloys for Jewellery at the 1999 Santa Fe Symposium, and this built on the information provided by Huckle. It sums up the alloys widely available and their application in jewellery at that time, with some comment on the new alloys being introduced, as we shall see in the table at a later slide. In this context, both Mertz and Huckle noted it is important to recognise the different marking standards of various countries at that time. Mertz noted European countries generally allowed only 950 fineness alloys, with some allowing no negative tolerance, some allowing a small negative tolerance, and others allowing iridium content to be counted as platinum within the 950 standard. In Germany, he noted that several fineness standards and alloys were allowed, as we can see in the table on the slide. In the USA, he noted that the standard for jewellery to be marked as platinum was 950 fineness, but the minimum amount of platinum allowed was 500 parts per thousand, with the rest of the alloy comprising the 950 parts per thousand total platinum group metals, and this with a zero tolerance. He also notes that 950, 900 and 850 fineness standards are allowed in Japan. This table shows alloys at 950 fineness that Metz noted. He notes, with regard to actual alloy compositions, that each alloy is made for specific manufacturing functions, as we can see on this table. For example, and there are different preferences in different countries. Table 2 lists the alloys in common or growing usage around the world with their function and countries of major use. He also lists separately a number of alloys that are specific to Japan. Mertz's list did not record the platinum 5% copper alloy except for its use in Japan, which has been mentioned earlier as an alloy commonly used in Europe. Mertz does note that in the USA, the most common alloys in use are 950 platinum with 5% cobalt or ruthenium and 900 platinum, 10% iridium. However, in an updated version of this paper, the platinum 5% copper alloy has now been included. This table shows the rest of Mertz's table at 900, 850 and 800 finenesses. As we can see, again, there are a range of alloys. These refer only to Europe and the USA and Japan generally. But in his book, Savitsky in 1984 notes that in the old USSR in Eastern Europe, only two 950 alloys are used. Platinum 5% iridium in Russia and platinum 4.5 palladium, 0.5 iridium in East Germany, the old German Democratic Republic. We can also note on this table some of the alloys that are specific to Japan. Let us look a bit at the technical aspects of these alloys. We note that at 950 and 900 fineness qualities, there is a broad range of alloys available to the jeweller, each suited to various manufacturing techniques. All have a good white colour, although some may benefit from rhodium plating, for example, the platinum 10% palladium alloy, to give a brighter, whiter colour. The main differences between alloys lie in their hardness or strength and their melting ranges. Batani has examined the microstructure of several platinum alloys and notes that many alloys are single phase, as one might expect from examination of their phase diagrams, particularly at 950 and 900 fineness qualities. We also note that some alloys are age hardenable and can achieve high hardness when in the aged condition, and we'll come onto that in a little later. In this slide, I show some of the alloying additions, some of the alloying phase diagrams where we can show hardening by heat treatment is possible. This is the aging treatments. Some alloy systems show large areas of miscibility gaps at low temperatures. Examples are platinum gold and platinum copper systems. And we show the platinum gold phase diagram on the left-hand side of the slide. And we can see the vertical red line, which is equivalent to the 5% alloying addition. And we note this line intersects with the line of the miscibility gap. Platinum 5% gold is the example that we're showing here. And we can get an aged hardness of 300 Vickers, leading to better scratch and wear resistance of jewellery. The centre phase diagram, the platinum cobalt phase diagram, formed an ordered in platinum 3 cobalt that just about touches the 5% cobalt composition line marked in red on the slide. Suggests that possibly there might be some slight hardening available by age hardening heat treatments. The use of gallium, as we can see in the phase diagram on the right hand side, shows the 3.5% gallium composition intersecting the limit of solid solubility, again demonstrating how we can use age hardening treatments to harden gallium containing alloys. And its use forms the basis of several heat treatable alloys, as we noted in the table. From the table of alloys, it is clear that some alloys are quite soft, with a hardness value lying in the range of 50 to 100 Vickers. Some have a moderate hardness value, hardness of 100 to 150 Vickers, and others are quite hard, with hardness in the range 150 to 350 Vickers. The higher values usually when in the age-hardened condition. In a recent study of customer complaints, it has been noted that the use of soft alloys is a significant factor in platinum jewellery becoming deformed in shape and bad scratch when worn by consumers, and wedding bands. Examples are pictured on the slide. The ring on the far right at the bottom has been deformed because the lady that wore it went to concerts very regularly and was clapping her hands very hard. And you can see the result. The melting point of pure platinum is 1796 degrees.
Vediamo il livello di fusione. Vediamo quello dell'argento, del platino. Vediamo che abbiamo delle range di fusione molto alte per il gaglio, come vediamo nella tabella. E queste leghe richiedono una buona attrezzatura in termini di fornace e anche una temperatura della lega piuttosto elevata. In generale, lavorare queste leghe non è un problema. C'è bisogno di una competenza particolare per avere una buona finitura e anche materiali speciali e diverse geometrie anche.
Tends to gall or adhere on the tool. The low thermal diffusivity of platinum alloys makes welding easier, particularly laser welding, compared to gold and silver alloys. Work around the turn of this century has demonstrated that microalloying of pure platinum and its alloys with small additions of calcium and or rare earth metals such as cerium, samarium and gadolinium, typically up to about 0.3%, can increase hardness substantially, but such microalloys do not appear to have been commercialized by the jewellery industry, probably because they are not easily cast or recyclable. This table, table 3, shows the higher melting the higher melting ranges and densities of platinum alloys. And we can note that gallium and indium additions, as we can see there, there's 3 alloys at the bottom of the 950 section, have lower melting temperatures compared to the other platinum alloys. And we note also the high density of all the alloys. The major manufacturing problems with platinum jewellery has been with investment casting. The high melting and casting temperatures require use of special phosphate bonded investment mould materials, and the poor melt fluidity requires use of centrifugal casting machines to obtain good mould fill rather than the modern gravity machines commonly used for gold and silver. The new generation of tilt casting machines are also suitable for platinum. The chief problem with platinum casting is getting defect-free castings, and there have been several investigations on the relative merits of different alloys, looking particularly at surface quality, form filling, and gas and shrinkage porosity. The general findings of these studies show that the platinum 5% cobalt alloy to be the best of current alloys, but it is still not ideal. Let us now look at progress in the last 20 or so years. There have been several studies to develop improved platinum jewellery alloys in the last 2 decades or so. These are focused on either stronger or harder alloys or improved investment casting alloys. Although alloys suitable for additive manufacturing or 3D printing have also been of interest. We will look at each of these areas in the following slides. Let us look first at stronger, harder alloys. The resistance of jewellery to abrasion and knocks, wear and scratch resistance, depends to a large extent on the hardness of the alloy. As noted earlier, a study of customer complaints showed platinum rings and wedding bands to be particularly prone to deformation of shape and to heavy wear, scratches and dents during customer service, i.e. whilst being worn, when they are made in soft or moderately hard alloys. Hard alloys tend to be difficult to work in manufacture, especially to set gems in mounts, and so it is advantageous if an alloy is relatively soft while being manufactured into a piece of jewellery that can be subsequently hardened to improve its durability while being worn by the customer. This can be achieved by age hardening, heat treatment of suitable alloys after manufacture. This is a treatment involving precipitation of a dense dispersion of fine particles of a second phase within the matrix grains of the alloy. For platinum, it has been noted that some current alloys are age hardenable, and alloys containing gallium have been developed specifically for this purpose. The first was the platinum 3% gallium 1.5% indium alloy developed by Johnson Matthey, and others have followed, such as the HTA alloy developed by Imperial Smelting in Canada, and the S alloys developed by Steve Kretschmer in the USA. Wiesner, in a paper presented in 1999, discusses heat-treatable alloys and notes earlier work at Degussa, at Hafner, Johnson Matthey, and by Steve Kretschmer to develop heat-treatable all ternary alloys, with many with melting ranges much lower than the conventional binary alloys, suggesting they all contain gallium and or indium additions. Such alloys are useful for their spring properties in springs and clasps, for example. Research carried out at Mintec in South Africa in 2005 has examined potential platinum alloy systems to identify suitable binary alloy systems that can be substantially age-hardened. Over 20 alloying metals were studied in the preliminary trials at addition levels of 2 to 4%. From this work, the best alloy was a platinum 2% titanium alloy, which had an as-cast and annealed hardness sufficiently low to be easily worked and formed, but with subsequent heat treatment, the hardness value could be increased by about 90 figures. Interestingly, there are parallels here with the development of 990 gold, which is a gold 1% titanium alloy. The Mintec work does not appear to have been further developed into a commercial alloy, possibly because it does not show much advantage over existing commercial gallium-containing alloys. More recently, a harder general-purpose alloy, True Plat, has been introduced to the market in the USA by Hoover and Strong. It's a 950 platinum ruthenium gallium alloy that is not age-hardenable. It has a high work hardening rate compared to 950 platinum ruthenium. And it has an annealed hardness of 180 vickers compared to 130 vickers for the ruthenium alloy. Look at improved casting alloys. The motivation here is to develop alloys less prone to casting defects, particularly casting porosity. Use of alloys with lower melting ranges to inhibit metal mold reaction is desirable too. Work carried out by Frié at Techform and Klotz and co-workers at FEM in Germany has focused on which alloys are best in terms of casting porosity, formation, form filling and surface quality, and establishing the mechanical properties of cast alloys. The use of computer simulation of the casting process has also assisted in optimizing process parameters in casting. Frié in particular has shown the benefits of a hot isostatic pressing treatment after casting in removing porosity from castings and improving the mechanical properties. What is particularly noticeable is the growing number of new platinum casting alloys that feature in these studies. And we will be talking about this in the next few slides. The alloy development started a little earlier than 2000 in 1997. Lanham of Engelhard, in a paper presented at the Platinum Day Symposium in New York, reported on a new investment casting alloy, 950 platinum copper cobalt, that combines the good properties of the platinum 5% cobalt alloy and the 5% copper alloys, and reduces the issue of magnetism in platinum cobalt alloy. Its as-cast hardness is about 119 vickers, a little lower than the platinum 5% cobalt alloy. Porosity is still present, and it had a tendency to form a surface oxide on heating. Another alloy development was presented by Norman Doe in 2000, in which he reported on a new 950 platinum hard casting alloy with an as-cast hardness of 160 to 170 vickers, which is much higher than the platinum 5% cobalt alloy. Little detail is given on the composition, but the discussion in the paper points to it being a 950 platinum gallium iridium alloy. A further alloy development was presented by Grice and Cart in 2002, where the development of a platinum gold X alloy, Plat Oro, is reported as an alternative to platinum 5% cobalt. This has an as-cast hardness of 125 Vickers, a little softer than the platinum 5% cobalt alloy, but it is non-magnetic and has lower melting range of 1590 to 1629 degrees Celsius. Grice has since reported that the Plat Oro alloy is actually a 5% gold copper alloy, but is no longer commercially produced. Frié and Fischer-Booner in their study reported in 2011 recognized the inadequacies of existing commercial casting alloys and widened their search to include 3 newer versions that contained undisclosed elements, which they designated as hard alloys. That is, they had a hardness of 175 or higher. The platinum cobalt X hard alloy with unknown additions appeared to show some promise. The platinum ruthenium X alloy is now known to be the platinum ruthenium gallium alloy from Hoover and Strong, and the platinum cobalt X alloy is a platinum cobalt indium alloy from Legor and is harder and non-magnetic compared to platinum cobalt. In 2014, Klotz and his co-workers at FEM in Germany utilized computer simulation of casting and thermodynamic calculations to optimize the process parameters of casting 5% ruthenium and 5% cobalt alloys, and was significant in that ternary alloys of the 950 platinum cobalt ruthenium alloys were explored, and they showed that improved form filling and surface quality resulted from additions of cobalt to platinum ruthenium alloys. The optimum amount depending on the casting technique used, centrifugal or tilt casting. In 2016, Mertz and Larg from Hafner studied 6 alloys which used tilt casting as opposed to centrifugal casting in their trials. 2 contained gallium or indium, and these alloys showed higher as-cast hardness and were rated higher in terms of castability. Each alloy had different strengths and weaknesses, and the authors concluded that no alloy in their study was perfect, but that progress was being made. It is noted that Hafner's patented an alloy 950 platinum gold indium in 2013 with the use of iridium or ruthenium as grain refiners. The largest range of alloys was studied by Frié and Klotz in 2018. They also measured the mechanical properties and wear resistance of castings. They warned against the use of soft alloys in cast jewellery and noted pronounced microsegregation in gallium and indium containing alloys, which increased micro-shrinkage porosity. Hot isostatic pressing treatments after casting eliminated porosity and restored the ductility. They also noted wear was related to hardness, harder alloys wearing less. No new alloy met all the requirements for casting. These studies and alloys that they examined are listed here in Table 4. Note the large range of alloys studied. There are new alloys that feature and are mostly at 950 fineness, but there are 2 at 900 fineness. These all have a range of hardnesses and melting ranges. This slide shows the mechanical properties that were documented in this study. And for simplicity, I only show the hardness values for as-cast and hot isostatically pressed alloys. So this gives us more detail. Ternary alloys featured. There is a range of hardnesses, but no perfect alloy is defined. A more fundamental approach to improve casting alloy design has been undertaken recently by Professor Glatzel and his apologies, by Professor Glatzel and his co-workers at the University of Bayreuth in Germany. They looked to develop an improved casting alloy of 950 fineness with the following requirements: a low casting temperature, a small melting range, a microstructure that is homogeneous, fine-grained in the range of 100 to 150 microns, and with low porosity. Hardness in the range of 155 to 170 Vickers for wear resistance and good ductility in excess of 30%. They also wanted good reflectance and a bright surface, and the use of alloying elements that are biocompatible and recyclable. In their study, their benchmark alloy was a 95% platinum, 1.8% copper, 2.9% gallium, which is a recent alloy development. They identified 25 possible alloying elements, and they ranked each element according to a suitability index. This comprised 4 characteristics: the maximum solubility in platinum, its hardness, the melting interval, and the liquidous change. They examined 2 sets of 5 alloys and tested them, and each contained up to 5 alloying additions. And these included elements such as aluminium, gold, copper, chromium, iron, iridium, manganese, palladium, rhodium, and vanadium. The compositions they studied are radically different from those alloys we've seen in the earlier slides. The compositions of the 2 most promising alloys are shown here on the table. 1A2 contains copper, iron, manganese, and chromium. The second alloy contains a little bit of copper, iron, palladium, vanadium, and yttrium. The hardness of these alloys, 164 for A2 and 165 Vickers for B2, is harder than the platinum cobalt alloy, and the benchmark alloy, the platinum cobalt gallium alloy they used, has a hardness of 225, quite a hard alloy. It begs the question, have these alloys been commercialized? And the other question that I beg is, with manganese and iron contents of these alloys, will it lead to a tarnishing problem? We saw that the use of manganese and iron when they were developing alternative white gold alloys without nickel and palladium, the Achilles heel was in fact tarnishing. So that's an interesting question we need to understand. Lastly, I'm going to talk very quickly about alloys for additive manufacturing or 3D printing. This is a technology that is attracting much interest in our industry, and the technique is known as selective laser melting. And this is where successive layers of alloy powders are selectively melted with a laser to build up a 3D model of the shape that's required. There is a lot of research taken on developing suitable machines, build techniques, and suitable alloy powders. It was very evident from the work that was done on gold for additive manufacturing that alloys need to be tailored to suit the selective laser melting process. You need to reduce the thermal conductivity and diffusivity and reduce the reflectance by adding alloying additions that better absorb energy and reduce local heat loss. This is because gold and silver have high thermal conductivities, and their high reflectance means that the energy tends to bounce off the surface rather than get absorbed. However, platinum and its alloys have much lower thermal conductivities, so making laser welding and selective laser melting much easier than gold and silver. There's particularly been a lot of research at ProGold on the selective laser melting of 950 platinum alloys by Damiano Zito and his co-workers. In a study they reported in 2014, they used a 950 platinum alloy but didn't give details of its composition. In 2015, they used an alloy which they said was a modified platinum cobalt alloy, a little bit different to the alloy they used in their 2014 study. In 2018, their study compared selective laser melting process to the same components made by investment casting, and in that they used a platinum copper gallium indium alloy. What became clear from all of these studies, manufacturing process, and there is no need to develop special alloy compositions for selective laser melting, which is in contrast to that what we've seen for gold. That is the end of my review of platinum alloys. So let's make a few conclusions. There's been an evolution and growth in platinum alloy compositions for jewellery over the last 100 years. The focus has been on developing alloys suited to the manufacturing process. There has been a major evolution in the last 20 to 30 years, particularly for investment casting application at the 950 finest quality standard. Investment casting of platinum alloys remains a major quality issue, particularly surface quality and porosity defects. It has been clearly shown that hot isostatic pressing after casting does remove porosity and improves the mechanical properties of castings. And lastly, the new technology of additive manufacturing does not appear to require special alloy compositions, unlike gold. Lastly, I'd like to thank Massimo Poliro and his staff at Legor for inviting me to present at the Jewellery Technology Forum. And I'd also like to thank many friends and companies in the industry for providing me with information and allowing use of their pictures and tables, including Johnson Matthey, Legor, ProGold, FEM, Platinum Guild International, Hoover and Strong, and Techful. Thank you very much.
Thank you, Chris. Si prepari il prossimo relatore.
Now the floor to the next speaker, Dr. Manuele Dabala, who will speak about the development of thermomechanical processes as an alternative to grain refiners in 10-cat gold alloys. He's an ordinary professor at the Department of Engineering at Padua University, and he works on the surface treatment on metals, corrosion, powder metallurgy, and production of metallic nano powder. More 100 publication, a member of the Italian Society of Metallurgy and the European Society. He's in charge of many projects to produce nanoparticles and surface treatment of metals. The use of grain refiners such as iridium and 18-karat gold is common practice. These elements have an impact on the cost of raw materials used. The aim of the presentation is to demonstrate that without refiners in an alloy, you can obtain similar results when refiners are used improving thermomechanical processes. You have the floor.
We presented my work on the development of thermomechanical processes as an alloy alternative to the grain refiners in 18 carats alloy. Because the aim of this study was to control the grain size of 18 carats gold alloy during the thermomechanical processes of the production of an hollow chain, avoiding the use of grain refiners. Usually in the production of many processes and the production of many objects in jewelry, it is used grain refiners because they, during the solidification, promotes the nucleation of the grains, and during the recrystallization they interact with the grain boundary of the refiner and avoid the diffusion of the atoms between the grain boundaries in order to reduce the growth of the grains during the process of recrystallization, during the annealing essentially. So the use of grain refiners is very popular because it is possible to obtain in as-cast condition the very small grain size, and it is very popular to use the grain refiners in order to control the grain growth during the annealing. As a constraint is not carefully use a lot of grain refiners because they tends to form hard precipitators that can control the grain growth during the annealing, but they can induce brittleness in the alloys. And moreover, the precipitation of hard precipitators, hard particles, can reduce the surface quality of the objects. And moreover, the use of grain refiners is expensive because platinum, iridium, ruthenium, and other like, for example, other grain refiners are very expensive, or in the case of cobalt, they can introduce magnetism in the alloy. So, why it is necessary to use grain refiners? Because during the solidification, there are two steps. The first step is the formation of nuclei, that is called nucleation, and the other step is the growth of this nuclei to form all the solid material. In order to obtain the nucleation, it is necessary two terms in terms of energy. One negative, that is the terms of free energy of volumetric, that is the passage from liquids to solids. And the other is the positive terms of energy, that is the creation of an interface between solid and liquid. As you can see in the picture that there are terms positive, that is the red curve, that is the solidification, the energy necessary for the creation of interface, and the blue curves, that is the energy necessary for the solidification, the free energy, negative terms, to create the solid. If you sum these two curves, two terms of energy, related with the radius of the nuclei, it is possible to find a critical radius, R stars, where the nuclei are stable if the radius of this nuclei are larger than the value of R stars. If you have nuclei with a radius lower than R stars, the nuclei are not stable and tend to redissolve. So, how is this critical size, and essentially what determines its size? The size of this critical radius, it depends on the surface energy, it depends on the melting point of the material, but essentially depends on the undercooling of the liquid. If the undercooling is higher, the radius becomes lower. So, if you have a lower radius, you have higher nucleation. But how is the range of this undercooling? And you can see in the right side of the picture that it is necessary, usually in a homogeneous nucleation, to have a very large undercooling to obtain a very high number of nuclei. If you have a very small undercooling, the nucleation is very poor and you have very poor, very low number of nuclei and a very large size of the grains. For this reason, it is better to introduce a surface that increases the wettability of the alloy and reduce the undercooling and promotes the nucleation. The interfacial energy will be reduced and the presence of surfaces introduce a larger nucleation. So what is this kind of surface? One is the surface of the mold, the other is the inoculants, and essentially iridium and ruthenium acts as welded surface during the solidification to facilitate the nucleation. Moreover, iridium and ruthenium reduces the interfacial energy for the nucleation of a gold alloys or other kind of precious alloys. The other term is the recrystallization. When we deform a material, and gold alloy, platinum alloy, which kind of alloy, during the plastic deformation, the alloys reduce the grain size. But the reduction of grain size is with increasing of the energy, of the internal energy of the alloys. Because during the deformation, part of the energy is absorbed of the alloys to reduce the grain size. But when the temperature of the alloys is raised, there is a behavior that is called recrystallization that produces the nucleation and the growth of strain-free grains. These strain-free grains reduce the tensile strength, reduce the hardness, not always, but essentially increases the ductility of the alloys. This is the process that occurs during the annealing. Okay? But what's happened? If the material, when is recrystallized, is further annealed, and the time at high temperature becomes larger, there is the formation of very large grains that grows from the strain-free grains. This because the grain boundary energy is reduced to the decrease in the grain boundary area. So it is necessary to increase the size of the material, of the grains of the material. So the grain growth involves the movement of grain boundaries, and it is important to reduce this grain growth in order to maintain high mechanical properties of the alloy, in order to avoid brittleness of the alloy. Okay? So, how is possible to reduce this grain growth? It is possible to reduce the movement of these grain boundaries. There is two possibilities. Or you have a second phase particles, and second phase particles decreases because it's a block for the grain movement, of the grain boundary movement. Or it is possible reduce the grain growth by reducing the diffusion, because these processes are processes governed by diffusion. It is possible to reduce the grain growth by the diffusion of the grain boundaries of the atoms between the grain boundaries, from the boundaries of adjacent grains. So, in order to, this is very important, especially when we speak about the production of gold alloy chains, or hollow chains. Because gold hollow chains and materials necessary for the production of chains hollow needs to have a very high mechanical properties, and they needs to avoid brittleness of the material. So usually the process to produce gold hollow chains is a first step of casting, a second step of rolling in order to obtain a rebound, and further annealing, further rolling, and so on. And at the end, it is necessary to weld the rebound with another rebound of iron, and usually to bend the material in order to obtain the chain that maintains a small fenditure between the border of the ribbons in order to remove the iron by acid etching. So in this whole production, it is very important to control the steps of annealing and the steps of rolling, because if you control the steps of rolling and the steps of annealing, you can obtain a very high quality of the surface and a very high mechanical properties of the alloy. So, in our work, we use as a reference alloy an 18 carats alloy, which contain, as you can see, 0.05% of iridium. We compare this alloy with similar alloys, 4N alloy, where the iridium is completely disappeared, and starting from these 2 points, we study a lot of alloys, but the best results that we obtain is with the alloy called alloy 2, where you can see that the composition is close to the alloys refined, but we change the composition in order to avoid the diffusion of the elements between the grain boundaries in order to reduce the growth of the recrystallized grain. You can see in the picture the alloy obtained in a horizontal furnace and a vertical furnace, but you can see the difference between a refined alloy that contains the grain refiner iridium and the grain size of the 4N alloy, the alloy 2. You can see that the size of the grains after casting are completely different. In the grain refined alloy, the size of the grains is very small. In the case of 4N alloy and alloy 2, the grain size is very, very large. But this is due because we don't have any kind of control on the nucleation. But we studied the process, the thermomechanical process, with the aim of this investigation. And you can see that the reduction, the section reduction obtained during rolling is more or less between 35% and 65%, with a medium of 50%. And the annealing was made at the beginning with, in a step at 660 degrees for 45 minutes each annealing steps. At the end, the spot welding, where it is introduced the iron ribbon, the iron foil on the gold foil, is obtained by a welding process, a spot welding process, with a current of 20,000 ampere, and after the welding, there is an annealing at 930 degrees for 2 minutes, only to reduce the, is a stress-relieving annealing. This is the result obtained after rolling and annealing in the reference alloy. You can see that the grain size is maintained more or less similar. You don't have any growth of the grain size during the annealing due to the effect of the grain refiners that acts as inhibitors of the diffusion of the materials between the grain boundaries. Moreover, you can see that after welding process and after the final annealing, the grain size is very, very low, and the mechanical properties with this kind of microstructure is very nice, is very high. There is a small variation in the size of the, or better, it is the size distribution of the grain size is larger after the final annealing than in the previous process. This is because the temperature is very high, and so it is possible to have an higher grain growth when you use an high temperature of annealing. This is the Vickers micro harness obtained after the different steps. You can see that at the end, after the welding process and the final annealing, the hardness obtained is very small, very low, and it is possible to obtain an alloy that is very tough. It's not hard, but it's tough. This is the results obtained with the 4N alloy. After the first rolling, the grains remains very large, only, but you can see that there are a lot of lines inside the grains that is an exhibition of the deformation obtained by the grains. And after the first annealing, you can see that the grains becomes lower, but rolling and annealing produce a reduction of the grain size. So this because the thermomechanical process was relatively good control. But I want to show you, okay. This is the results obtained with the alloy 2. After the first rolling, the results is more or less the same of 4N. But as you can see, after the second annealing, you can see here that there is, after the first annealing, the distribution of the grain size is very large. You can see large grains and small grains in the microstructure. And also this is maintained, but in smaller range, in lower range, after the second annealing. Instead, you can see that in the alloy 2, after the first annealing, we have also a large distribution of the grain size, but this is not maintained after the second annealing and also after the third. Why? Because the change in composition reduce the diffusion of the elements between the grain boundaries. So thanks to the control of the temperature, the time, and the composition, it is possible to obtain after the mechanical process good results in terms of homogeneity of the grain size. And in fact, you can see that, for example, the grain size after the second annealing and after the final annealing, for the alloy refined and for the alloy 2, that is the best, they are very, very close. Instead, the grain size of the 4N alloy, without any control with a reference in composition, the grain size is more inhomogeneous, and you have a lot of large grains and small grains. The hardness also is not so different for all the alloys after the process. This is because usually in this kind of alloy, the terms of hardness is not so important. It is better to refer the alloy not in terms of hardness, but in terms of toughness. Because when you have the hardness, as you can see, it's more or less the same. But the microstructure is completely different. And so the hardness is not a parameter to consider in this in this kind of production. It is better to consider the toughness, the brittle, the resistance of the alloy to the deformation. Okay, that is obtained by the small grain size. Smaller is the grain size, higher is the mechanical properties of the alloy, but not the hardness. The hardness doesn't change. The colors of the alloys is more or less the same, usually with a colorimetric system based on syllab system. When the difference is more lower than 3, the colors is not appreciated by the human eyes. So the alloy refined and the alloy 2 have a color that is more or less the same. We study also the corrosion resistance because we changed the composition, so we wanted to see if the corrosion resistance in artificial precipitation is the same, and in fact the results is more or less equivalent. Okay, oops. After that, we try to investigate how to improve the quality of the microstructure, reducing the inhomogeneity of the grain size. In alloy 4N, it is possible to see that after 15 minutes, the recrystallization is not completely obtained, but after 20 minutes, all the recrystallization is obtained, but the grain growth starts. In fact, after 20 minutes, you can see that there is the grains with large size and grains with small size. So the recrystallization is obtained more or less in 20 minutes, but the first grains that recrystallize starts to become larger because they grow, because there are no any control of the flows of the elements between the grain boundaries. Instead, and so you can see that the hardness doesn't change. You can see that the hardness, if you change the temperature and you change the size distribution, the hardness doesn't change. But the grain size increase with a very high, with the temperature, with the time. Instead, if you consider the annealing of the alloy 2, you can see that the microstructure is completely recrystallized after 15 minutes, and after 20 minutes, the homogeneity of the grain size is more or less acceptable. And it is maintained till 40 minutes of annealing. After 40 minutes of annealing, you have that the grain size starts to growth, and you have the not homogenization of the grain size. Also, this is the evolution of the average grain size with the temperature, with the time of annealing, and you can see that the hardness doesn't change with the time, but as you can see, after 5 minutes, you have that part of the grains are not recrystallized. In fact, in the picture, you can see that these large grains is a grain deformed. The small grains at the boundary of this large grain are grains that are strain-free, that starts to nucleate and grow. So, in this picture, you can compare the behavior of the annealing time in relationship with the average grain size. You can see that controlling the composition, you can obtain a better quality of the alloy, because the grain size of the alloy number 2 is smaller with the same temperature, with the same time of the annealing than the 4N alloy. And it is, if you maintain the annealing time in less than 20, in more or less 20-25 minutes, the size of the grain size is not so higher than the refined alloy. This is the Burg thermal analysis, and you can see that there is a very linear correlation between the grain size and the logarithm of the time of the annealing. This is a parameter to consider and to realize a correct annealing process. So, in conclusion, I was fast, so we recovered some time. The iridium in 18-karat alloys increase the price of the alloy. So if we remove the content, if we remove the refiners, we have an increase in the crystal size after casting because we don't have any control about nucleation. So in this case, the grain refiners are really necessary for process of casting. But in the case of process of deformation, we have demonstrated that maybe they are not necessary. In the case of casting, they are surely necessary because if you don't have grain refiners, the grain size after casting are not acceptable. Okay, is not acceptable. But in the case of deformation of the alloys, this could be avoided. In fact, in the first annealing, the not refined alloys show a strong reduction in the crystalline dimension, in the grain size, but they maintain some inhomogeneity. However, after the second rolling and after the third rolling and after the further annealing, the process and the grain size can be maintained at level acceptable for the production, and it is possible to obtain an alloy that can be used in the production of hollow chains without the use of grain refiners. That is all. Thank you very much for the attention.
Grazie, Dottor Davala.
Thank you very much, Mr. Davala. Let's move to the next speaker, who is Florian Barling. Professor Florian Barling will speak about progress in titanium investment casting. He has a degree in engineering and works at the Institute of Research on Precious Metals and Metal Chemistry in Germany, and he performs applied research. Titanium alloys are known for low density, high mechanical strength, high resistance to corrosion. These exceptional properties are complex to apply because of the difficulty of using them during production, because titanium is highly reactive. Here, he compares different ceramic materials to be used as crucible and the opportunities offered by innovative ceramic materials. You have the floor.
Welcome to my presentation about the progress in investment casting. Thank you for the introduction. It's a project It's a project together with the Institute of Ceramics, Refractories and Composite Materials from the TU Freiburg in Germany. To give a short outline, I want to say something about the motivation of the project, followed by the new material we tried to fix this problem and the challenge. Then the experimental part where to show some casting trials we did. And finally the results we received with the casting trials. And I will close with a short summary and outlook. What is the motivation of the project? As you can see here, there are several applications already used out of titanium, like jewelry parts, rings or watches are already produced, as well as medical applications like teeth crowns or hip implants. And also a technical application because of the high toughness of the material. It offers good properties for these applications, and it's a very interesting material for these kind of applications. But at the moment, most of them are produced by chip milling or grinding, and we try to improve the casting process to get a easier near net shape production of the more complex parts. But at the moment there's a lack of resistant crucibles and shell modes, making the casting process difficult. As you can see here on the picture, on the picture, this is a commercial crucible we tested in comparison to our product. And as you can see here, there's a dissolution of the coating. It's a coated crucible with yttria. And this damage causes very great impurities of the metal you cast with this crucible after one shot. So even with if the crucible is new, you get impurities due to dissolution of the coating. So this was one aspect we tried to fix to improve the crucibles. Another part is the shell mode, where the melt is casted in, and at the moment, state of the art is the reaction zone and the surface of the cast parts, consisting of a typical, on the experts known alpha case. It's a hard and brittle surface layer, and it's, in the better case, you want to avoid this surface layer because it makes the mechanical properties lower and not appropriate enough. So we tried to fix this problem with a new material, as it's called calcium zirconate. You can see here the phase diagram. It consists out of two refractories, which are for its own, each of them for its own is very thermodynamic stable, but not in case of titanium. Titanium melt needs special resistance, and so we combine both of them to form the interceramic phase called calcium zirconate, and this offers good properties to cast titanium to produce crucibles and shell molds out of this material. It has a high melting point and a good resistance, corrosion resistance. Now the examinations we made with this new material. You can see a typical production of shells we made in this project. It began with the production of the slurry, mixing powder and some liquids to get a dip fitting slurry. Then we dip the wax models inside the slurry to get a shell mold step by step. 6 layers were performed in such way, and between the layers there's sanding and drying taking place. After the shell mold is completely coated, the dewaxing process starts, and after the dewaxing you got a hollow shape you want, and sintering of the material is necessary to get a better mechanical stability. And finally you can cast the metal, in this case titanium 6-4. We used the titanium alloy, the most used titanium alloy for casting trials. Our project partner, who has a good experience in refractory preparation, performed these crucibles for the project, and it's produced by a cold isostatic pressing of a press mass, and afterwards sintered at 1,650 degrees for 5 hours. You get a good stability, and it's optimized for our casting machine. We were able to cast with this crucible about 500 grams of titanium. This is the casting machine we used. It's a tilt casting machine from the company Endotherm, which is also a company in our committee, project committee. And the benefit of this machine is the dual chamber principle. We have a crucible chamber and a mold chamber, and we can press the mold to a tight ring, and so we get a two chamber system where we can set a different gas pressure on it to get a faster filling and more pressure on the melt to get a better form filling. Yeah. We not only tried this way of producing cast parts, also a different machine was used, like centrifugal casting. And this needs a special ceramic, special crucible shape. As you can see, it's a more complex shape. And it wasn't possible to produce by cold isostatic pressing, so we need another way to combine our new ceramic material with this shape, and we decided to make a slip casting of an existing crucible out of aluminum titanate. That works very good in case of stability and slip casting. We got a tight layer, front layer, inside the crucible, which was sintered at 4,150 degrees C. But as we recognized later in the casting trials, this crucible wasn't as stable as the massive one. This is the casting machine we used for this type of crucible. It's a centrifugal arm with a contrary weight to balance, and here's the crucible with the liquid metal inside. It's an inductive heating process, and here's the shell mold placed in a steel ring, and when the liquid is the metal is completely melted, the coil falls down, and immediately acceleration of the arm takes place, so that the centrifugal force led lead the melt inside the shell mold. Here we have very high acceleration speeds of 400 rounds per minute per second, what is nearly the maximum of the machine. Now we come to the parameters we determined for which are the best for the machines we used. Overall, it is important to get a fast filling because titanium with a melting point of over 1600 degrees C pretends to freeze very fast inside the mold if you don't manage it to bring it fast inside it. So we decided to overheat or to preheat our shell mold to high temperatures, even more at the tilt casting machine, because the filling is a little bit faster than with the centrifugal casting machine. So we want to improve the form filling with this. We increased the heating power from a low level to a higher level in both cases. This should avoid the melting an early state of the heating process in the bottom region of the crucible, because when the liquid phase exists inside the crucible, the reaction is more intense than in solid state. And so we want to keep this time, I call it the exposition time, very low, because this is the time even this good material reacts with our melt. The tilt casting machine was equipped with a better vacuum pump stand. They are 2 rotary pumps in line in a row, and it's especially designed for titanium casting, whereas the centrifugal casting machine wasn't as normally used for precious metals, so not for titanium, but we tried it to check the form filling and the reaction with the ceramic, not even the reaction with the atmosphere. So the melting pressure was nearly the same around atmospheric pressure. The temperatures we used were 150 to 200 degrees overheated over the melting point, superheating, and the exposition time, that means the time where liquid phase exists in the crucible, was between 30 seconds and 5 minutes maximum. The tilt speed and the acceleration and rotation speed was set in both cases to maximum of the machine capacity to get a fast filling, as said before. So the results we achieved with these parameters, you can see here with the commercial crucible. We tried to compare it. Shows impurities inside the material, the cast parts. After the casting process, you can see net-like shape of precipitates. These are yttria inclusions and come from the front coating of the crucible. You get decrease of the mechanical tensile strength and embrittlement of the material due to that inclusion. So this is not good for the material. The contents, the impurity contents, you can see here. It's very high. In case of titanium, it's only allowed, according to ASTM standard, a maximum of 0.25 oxygen. On the contrary, a cast part examined produced with our crucible is showing no precipitates. This is alpha beta microstructure. But even with this material, we got impurities of zirconium, but they don't build precipitates. Why this is the case, you can see in these phase diagrams with the zirconium. On the left side is titanium, the titanium-rich side. On the right side, the zirconium-rich. And as you can see, there's a completely solubility of zirconium inside titanium, and so no precipitates will form during the cooling process. When we have a look at the right side with yttrium, titanium here and yttrium here, we have a gap, a solubility gap between them, and separate phases on both sides. And so we got precipitates due to a bad solubility of yttrium in titanium. Then we developed a reaction scheme beginning with calcium zirconate as our refractory material. The reaction takes place in form of a dissociation of into zirconia and calcia, which were both reduced to its elements, zirconium and oxygen, as well as calcium and oxygen, which are nearly all diffuse into the titanium melt. Only the calcium evaporates due to high temperatures and weren't present in the later cast part. To get a connection of impurities in the cast parts with our casting parameters like temperature and exposition time, we tried to implement a new parameter which is called LMP parameter, which is originally used to describe to approximate experiments to high temperature creep processes from Mr. Miller and Mr. Larsen. And we changed the equation in this form that we set our melting temperature, the big T, in the equation, and the small t is our exposition time. And so we can calculate a value which should describe the stress for the refractory material and therefore the impurities and the quality of our cast parts. The results you can see here. This is a graph where the LMP values are on the x-axis and the concentration of oxygen and zirconium on the y-axis. And as you can see, there's the correlation between these two values visible, which can be separated into two sectors. And the lower sector of the LMP values, there's a stable area where no reaction or very low reaction takes place, and a good casting quality is achieved. When we cross a certain lane at a certain value, the impurities increase very fast, which means our ceramic reacts stronger with the melt due to higher temperature time relation. You can calculate with a certain LMP value the time and temperature which is used to produce this cast part. This was for the first. This slide was for the massive crucibles at tilt casting machine, and now we come to the coated crucibles with calcium zirconate and the centrifugal casting machine. As you can see, we have no plateau in this case. From the beginning of heating, we got a strong pollution of our melt due to reaction. That means that the coating isn't stable enough and can resist a reaction. So the limits for ISTM couldn't be met, and the values are much higher than the feedstock material was. We also measured the hardness of the material, and we recognized that with the increasing oxygen content, the hardness values also increase, which is already known in literature. These are typical cast parts we produce, and as you can see here, we compare two cast parts, one produced with a already existing shell mold and one made with our calcium zirconate shell mold, and the difference is clearly visible. Here we have a black surface with ceramic residue sticking on it, and here we have a golden shining surface. There are also residues of the ceramic visible, but the reaction looks very weaker than on the right side. When you go into the deep of these parts, that means we make cross sections of some casting parts. Then we can see that this below the surface it looks also different. With our calcium zirconate shell mold, we got a reaction zone, a porous reaction zone, which comes from the dissolution of calcium zirconate, and because of that we have also a diffusion zone, but we can't see it because no phase transformation took place. On the other side, the commercial shell mold showed the typical alpha case. As mentioned before, this is very hard and brittle and needs to be post-processed by sandblasting, for example. When we measured the hardness from the core to the edge of the parts, to the surface, we recognized that increase in hardness in correlation with the oxygen content is visible in both cases, as well as with calcium zirconate as a shell, as well as the R&R shell. But even with the yttrium shell, we got higher hardness level on the corner of the cast parts, whereas with the calcium zirconate we got not this high values. Here you can see some typical parts we produced, like tensile probe samples, trees, jewelry parts. The surface is very filigree, the shape of the part is very filigree, and the quality of the cast parts is very good. To summarize my presentation, we tried a new ceramic material for investment casting, for producing investment casting products, crucibles and shell molds, and make some casting trials with them. We detected a reaction with this material, but it was less than with the existing products, and we developed a reaction scheme and analyzed the reaction behavior and tried to get a connection between our parameters, our casting parameters, to the quality of our cast parts, and therefore we fixed out the important factors, the exposition time and the maximum temperature of the melt. These are the most important factors during the casting process, and we implemented a new parameter where we calculated with these values a parameter value who should allow, who should give a guideline for good casting quality. And with the shell mold, we got a better surface quality and low reaction. To give an outlook, in the future we plan to make a flame spraying of calcium zirconate to allow the coating of different types of materials, different ceramic materials with calcium zirconate, make it more flexible. Also we continue to optimize the casting process, and finally we want to upscale it for industrial application. Now I want to acknowledge our project funding, IEF and EGF, and our project committee, which consists of several companies out of Germany. Thank you for your attention.
Thank you, Dr. Barling.
Bene, con i prossimi due interventi apriamo l'ultima sezione.
Now we move on to the third session, 3D additive manufacturing. A historical speaker at JTF, Dr. Ulrich Klotz, who speak about additive manufacturing of platinum alloys. He got a degree in engineering on physical metallurgy at Stuttgart in Germany. and a PhD in material science at HT Zurich in Switzerland. He is the director of the Department of Physical Metallurgy at the Research Institute on Precious Metals and Metal Chemistry FEM in Germany, in Schwagingen. The production of additive manufacturing of platinum alloys is at the center of increasing interest. On the one hand, because platinum implies challenges on traditional technology, and then because it's good to do 3D laser printing. The study analyzes the effects of the interaction between laser and platinum alloys at 9050 with different alloys. You have the floor.
Thank you.
Thank you very much. So thank you very much for this kind introduction. I'm very happy to be here and meet some of my friends and colleagues after these 2 years. And it's my pleasure to present you some results about the additive manufacturing of platinum alloys. We heard already about the possible alloys that are available for platinum, and also some general remarks about additive manufacturing in the talk of Chris Corti. And so this helps me to continue with that topic. I want to show some practical aspects during the laser powder bed fusion melting of jewelry items. So I will start with a short motivation, show our experimental procedure, our results, and summarize my talk. So I mentioned laser powder bed fusion technology. We've heard about selective laser melting. Some people speak of laser beam melting. These are different names for the same technology. The principle is that you apply a powder bed in a machine. The powder bed has a layer thickness of 20 to 50 microns, sometimes for steels even higher. And this powder bed is melted at some positions with a laser, and so the part is melted layer by layer because the platform is lowered each layer. So this has some benefits and drawbacks compared to investment casting techniques. We have shorter process cycles. We can produce parts faster. There is a reduced amount of precious metal required because we don't need to cast a tree and sprue. Fewer consumables are needed, and we get comparable roughness and porosity as previous studies showed. But of course, there are also some drawbacks. So this is a very simplistic comparison. We have much higher machine costs, higher costs for metal powders and supplies. And well, the last point is actually not really a drawback. We need alternative design for such parts, but actually this is also a benefit of these 3D printing technologies, that we can realize alternative designs by 3D printing or LPBF process. So what did we do in our study? We wanted to know about the effect of the alloying composition, and to study this we used sheet material. So we prepared small metal sheets that we put into our machine, and we applied laser tracks on these machines. Because this is much easier than producing a powder. Producing a powder means a very large effort. You need a relatively large amount of metal to melt, and therefore we went this way by using these laser tracks on sheet material. Then we used a commercially available alloy by C. Hafner to do some laser powder bed fusion experiments. We did a small parameter optimization, and I will show you an example about how the support structures are influencing the result that you obtain. And we did a small optimization of such support structures. And of course, we did the characterization by microstructure and porosity and manufactured some jewelry items as examples. So this is our approach on using the laser tracks. This picture shows you a platinum alloy sheet with different laser tracks. We use different compositions, binary and ternary alloys, and several 950 platinum ruthenium based alloys. And you see the laser tracks have different thickness, which is depending on the laser speed. All tests were done at the same laser power. So the smaller the speed, the wider the laser track, because the more energy per time unit is applied onto the material. So we measured the width of these laser tracks, and also did cross sections to measure the depth of the laser tracks. Well, of course, the way how the material reacts depends on its physical properties, and these are the melting range. Usually the lower melting, and the wider the melting range, the wider the depth is, and the wider and deeper the laser track is. The same is true if the reflectivity is influenced, or if the thermal and electrical conductivity is influenced by the alloying elements. Now here's an example how the laser width, line width of this laser track depends on the laser speed. So we see with what we see already on the picture, that with increasing laser speed, the laser width is decreasing, and the process gets more stable, because the scattering of so this is the maximum and minimum values. It's shown by the color range. The scattering is reduced. And here we see a cross-section. So you see the sheet material, the deformed sheet material, and here you see the cross-section of the laser track. So we measured these values, and we see an effect of the laser material interaction. There are two principal modes that are distributed, which is the conduction mode and the keyhole mode. I will show you an example how this looks exactly here. So here we see a very small laser track with low depth. You see the scale is 40 microns. So this is a typical example for the conduction mode. This is done in a 600 platinum alloy with palladium and copper. And if the copper and palladium ratio is exchanged, so here we have 300 palladium, 100 copper, and here we have 100 palladium and 300 copper. So the copper-rich alloy shows a much deeper laser track. This is a typical example of the keyhole mode. So here the scale is even higher, so this laser track is really much deeper. And if we plot the width and the depth, so the blue points are the depth, which are determined from the metallographic section, and the orange points are the width. We see the width is more or less constant, but the depth is increasing, and there is a maximum at around 20 to 30% copper in this platinum, copper, palladium alloys. So we see that the alloy composition has a strong effect on the depth of these laser tracks, and this is important because we have to melt layers together, so we have to assure that each layer is melted perfectly to the layer below. But on the other hand, if the energy input is too high, we can get porosity inside the material during the keyhole effect. Now here are some other examples. We used several ternary alloys. These are based on 950 platinum ruthenium. And in this first graph, I show some examples with high melting additions. So we used copper, cobalt, gold, and replaced some of the ruthenium. So on the left side, there is the platinum ruthenium alloy, and on the right side, there is the platinum copper, the platinum cobalt, platinum gold alloy. And we see that, if you look at the triangles, the depth is not affected by copper, but we see an increased depth if we add some cobalt or gold to this alloy. So we have not fully understood what is the reason, the physical reason for that, but I think it's an effect on the solidus and liquidus temperature that results in a certain melting range by adding these alloys. So I think these are interesting results when it comes to a fine optimization of the alloy composition for such applications. Now if we use some low melting alloy conditions like gallium, indium, tin, germanium or zinc, we get very different effects. So here we used a series of 950 platinum alloys. They contain 20 copper and 10 ruthenium, and then the copper was replaced by other alloying elements, or additions were made. Additions were made of other alloying elements, and we see that the width and the depth are influenced by some. So here's the platinum ruthenium copper alloy, and we see indium, zinc have little effect. We also see this here. There's very little effect. But other alloying elements like tin, germanium, or gallium, they have a very strong effect. We get this keyhole mode if we add germanium. In the case of gallium, we also get the keyhole mode, and we get a lot of cracks. So there are some critical alloying elements. So we heard about the H-hardenable alloys in the presentation of Chris Corti that contain gallium. So I suppose that they might be critical in the processing with the laser powder bed fusion or SLM process, because we have they lead to so-called segregation. So certain elements are concentrating in the liquid phase and strongly reduce the liquidus temperature. So this means we have a liquid phase remains and results in cracking during if the cooling is continued. However, indium and zinc show no effect, so that's was a bit surprising for us, but that was the observation that we also confirmed when we worked with alloyed powder. So in the second step of the study, we used alloyed powder. I already mentioned it's a commercial alloy powder, platinum gold indium alloy by C. Hafner in Germany. And from this alloy, we built little test parts. So these are a wedge type sample with some wires of different thickness, and with a small plate with different angles. So we want to simulate some structural features of jewelry objects, and there we did a parameter variation. You see that depending on the parameters, you can get very different results in terms of porosity. We determined the porosity by looking at this blue area marked here, and we measured the porosity by optical metallography And this is a plot of the porosity as a function of laser parameters. We've changed the laser speed as a function and measure the porosity, and we also changed the so-called hedge distance. The hedge distance is the distance between two laser tracks. The laser is going forth and back to scan an area, and the distance is called hedge distance. And we see that the hedge distance has actually a quite strong effect on the porosity, especially at higher laser speeds. We see that with decreasing hedge distance, the porosity increases. And this is probably due to an overheating, because more material is melted several times. While an increasing laser energy is also increasing the porosity. And this is increasing laser speed, sorry, and increasing laser speed is also increasing porosity, because if the speed is too high, the energy is missing. So anyway, we found very low porosity values. So this is 0.2% of porosity, which means 99.8% density. And it's easy to obtain values below 1%, which would be here. So we can obtain values of 99% density, which is more than comparable to cast platinum objects. We heard also in Chris Corty's presentation. And it's also, the porosity is much lower compared to 18-karat gold, where we have, with our machine, under comparable conditions, we achieve porosity levels of 1 to 2%. So now we built some ring samples, some typical jewelry samples for stone setting. We used this type of support structures. So here you can see our small test piece. And if you look carefully, you see that something is wrong here at the right side of the ring, but only on the right side. So if you look in detail, we see that the surface is porous here, and some material is missing. And of course, this is a non-acceptable defect. And we looked at the surface. We made a build shop and interrupted here at the critical height, and then looked at the surface of the ring shank. So this is shown here in these pictures. So here the left ring shank looks very good. The surface is perfectly lasered. There is no roughness, very low roughness. While on the right side we see so-called balling. So we get little droplets of melt. We get a large porosity. If we look at the cross-section in the metallography, we see very large pores. And this is a clear indication of overheating. And we were wondering why this is the case, because both sides were processed with the same parameters. And at the surface we also see later a certain roughness. So if we look here at the surface, we see a very porous, spongy surface. It looks like some material was there as a vapor and condensated on the surface. And we also see some hot cracks which can occur as an effect of overheating. This is the condensate in detail, how it looks, and this is an elemental map, so it shows the distribution of platinum, gold, and indium. So all elements are present in this condensate. It's clear that it's coming from the alloy, and especially the indium, which has a very low melting point, is concentrated. So this again confirms the overheating of this area. So why is this happening? This is our 3D model of the ring with the structures. And on the right side, we see a sketch. We applied the powder from the left with a wiper, and we also start lasering from the left, and then we see if on the left side when we start lasering, due to the geometry, there is solid material below, so the energy can be dissipated into the ring shank, while on the right side, in the very beginning of the laser process, there is a powder bed below this region. So the energy cannot be dissipated, and therefore we get this overheating. And the solution is to optimize the heat dissipations by applying suitable support structures. To do this, we analyze the ring geometry. Usually, a rule of thumb is all areas that have an inclination of lower than 45% need support. So this would actually only be this area. But we found from the analysis that on the left side we have about 60% that need supports, and on the right side more than 70 degrees angle needs supports to avoid this superheating. So we need much more supports than just supporting 45-degree angle. And if we analyze the CAD file and which are the regions that show angles of 60 or 72%, we mark them all in red, and we see that we need more supports on the right side compared to the left side. So we applied such supports, and this was the original parameter with the defect here. Then we used the new supports. You can see them here, and this could fully avoid the problem of the overheating on this side of the ring. Now let me summarize my presentation. Such laser track experiments are good to easily evaluate the effect of alloying elements, because you can easily prepare them and not much material and effort is needed. We see that some elements are critical. Gallium, tin, germanium, they increase the melting depth. They are critical in terms of hot cracking. And then in terms of the alloyed powder that we used, we found that we can achieve very low porosity levels over a wide range of process parameters. However, it appears important to do a proper heat management of the part, so it requires a careful analysis which regions need support structures, and this is especially important if you have many different parts that you want to produce. So there are rules of thumb, but it's better to test them if they are working for your particular part. So with this, I want to thank you. I want to acknowledge my colleagues that contributed, also the funding from the German government, and I thank you for your interest.
Bene, siamo arrivati all'ultima memoria di questa.
Well, we are at the end of the morning with the last paper. Then, after that, you can ask questions to speaker.
Allora, il prossimo ultimo relatore di questa mattina.
The next speaker is Carl Burkhardt. Sorry for my pronunciation. PhD in metallurgy and material in Birmingham. He is a professor of production technology and director of the Institute for Precious Metal at Fordham University. lithography-based metal manufacturing of jewelry and watch cases in 316L stainless steel and titanium alloy is the title. The LMM process is described, which is a 3D printing innovative system based on metal powder charged with a photopolymeric binder. It's very good for 316L stainless steel and titanium alloys, which are mainly used in the watch world because they allow high accuracy. You have the floor.
Morning. Thank you very much for the nice introduction, and I'm terribly sorry not to be there. I was hit by COVID on Wednesday evening, so I had to cancel on short notice, and I hope that we can do this online. I also got the difficult task to do a talk just before lunchtime, and I was also given a 20 minutes delay, so I will try to keep it as short as possible. I will talk today about lithography-based metal manufacturing of jewelry and watch cases made from stainless steel and titanium alloys. However, the process we developed is also suitable for precious metals, and we are currently in the development phase of doing so. Because I'm the first time at Vicenza, or would have been, I prepared a little advertising break about the University of Pforzheim and also our institute, but given the time that we have, I will jump over this. It will be in the proceedings. Just a little bit about our institute. We are part of the University of Pforzheim. We are standing on 3 pillars. One is we are partner of the regional precision engineering industry, where we're doing concept research, serial inspection, damage analysis, and so on. And here we have a very nicely fully equipped lab. And we are also, we have 2 research aspects. One is the recycling of rare earth metals and permanent magnets. That's a bigger one. And the second one is additive manufacturing of metals. For that, we have a couple of projects with a budget of over 30 million currently. And we are nicely equipped also for the additive manufacturing to cover the whole process chains. And in that circumstance, or in that framework, we developed a completely new additive manufacturing process, which is based on lithography. And Dr. Klotz already said that with laser powder bed fusion, there are a couple of issues that have to be solved. One is the heat dissipation. The second is that you always need support structures, which have to be removed afterwards. That during the very inconsistent heat distribution, you're very hot where the laser is, but should be cold where the powder is. That's not to be fused. You also have thermal stresses, and this also leads to a lot of after treatment and rework that has to be done. And the process we developed is based on avoiding all these issues. It's based on vat polymerization. Most of you will know it as stereolithography. I come to that, why it's working to make metals with stereolithography. But the outcome is that we have very good surface characteristics. So far, we don't see any method that is as good with that. We have a very good geometrical precision. We have no thermal distortions in the material. Currently, we work with stainless steel, with tool steels and titanium, but as I said, we are currently working or starting also with precious metals. The whole procedure is also suitable for non-weldable material, which is important if you want to do material mixtures. The printing speed is about 16 cubic centimeters per hour. That's not very much for industrial purposes, for large scale, but it's very interesting for small scale and also what we think for the jewelry production. There's one big difference compared to laser sintering. It's only suitable for small and very small parts. Currently, the rule of thumb is around 30 grams, but that's, of course, depending on your material. 30 grams of titanium are obviously much bigger than 30 grams of gold. And it's suitable for small and moderate quantities. How is it working? It's not as laser powder bed fusion a direct process where you get directly your part when you print it, but it's a so-called indirect or sinter-based process where you first print the green part and then remove the plastics. So you start with the CAD or scan data, you do the printing, and then we have a special procedure which I show you in a bit, which is the unmolding and the cleaning of the part. Then you get a green compact which goes into the sintering furnace, goes through a certain shrinkage, and then you have your LMM part, or lithography-based metal manufacturing part, because that's such a monstrous word, we call it LMM. So the machine itself looks like you see on the slide, and the material is a very special sauce, we call it. It's a mixture of metal powder and a photopolymer. And the metal filling ratio is between 55 and 60% of weight percent of material. The consistency of the whole material is best compared to butter, which means at room temperature, it's solid. If you cool it down, which we do in the printing chamber, it's nearly hard, as it would be a very cool butter block. But if you heat it up over 50 degrees, it gets very low viscosities and it's really water-like. And this helps us to apply the material. So what you do, you have a feedstock reservoir, which you see here. I don't know if you see my mouse pointer. I'm painting on it. If you don't see it, the feedstock reservoir is written here. There, the material is deposited. Then we have a heated wiper blade, which is heated up to 80 degrees, which liquefies the material, and then you can make a very fine layer of this slurry, of this mixture of the polymer and the metal. And then in your print chamber on the build platform, you expose the whole thing with UV light, with a DLP projector from above, and then the material hardens where it's struck by light. Once you have exposed one layer, you go down one and do the next one. And the result is a green compact, which is embedded fully in this building material mass. So that's a representation. Material is taken from this reservoir. It's put on the build platform, which was in red. Then it's exposed with ultraviolet light. It's hardening. And once this is finished, and it's real time what you see here, that takes quite a while, the next layer is applied again, and the procedure starts once more. So in the initializing phase, which you see on the picture of the left, you have a very clear, a very smooth surface because it's liquid and because it's water-like in its melted state. You don't have any kind of printing lines or scratches in the surface. And then you expose the whole thing here again, a video representation. So this coater puts a new layer of the material on top of the build platform. Then the DLP projector will expose the material. In this case, you will see two watch dials, which are done. And because you're exposing always the same surface, you can expose one layer with multiple materials at the same time, which makes the printing quite efficient. And this means, despite we have such a small build chamber currently, which is about the double size of a business card, you have a highly efficient printing process because you can use that build space really in a maximum, because almost any arrangement of identical or different parts in the build space is possible because there are no support structures required. Due to this consistency of the material, this butter-like structure, it's supporting the parts that are directly below. So as you can see, you can make multiple layers of different parts or of the same parts at the same time. So once your print job is finished, which can take a couple of hours, usually we do this overnight, you remove this material block. And again, I think the analogy of a butter block is quite nice because it's a solid block. You put it on a net, which you see in the middle, put it in an oven at 80 degrees. Then the non-exposed material liquefies, and the exposed samples, the green parts, which are solidified, they remain on the net. The other material you can directly reduce, but you have to mix it again because there are certain tendencies to demixing. So it's mixed again, but in general, there's no material loss at all, apart from what's remaining on that net and what's remaining on the surface. And you see the surface is kind of slurry-like. So what we do, we put in ultrasonic baths with some special cleaning agent for a couple of minutes, and then you have your green parts. These green parts, and then it's why it's called sinter-based additive manufacturing, is going into a sinter furnace. And first we do a thermal debinding. This is usually done under protective atmosphere, which could be argon, helium. No, not helium. It could be argon, nitrogen, or hydrogen. Helium would be far too expensive. It would work, but that's kind of pointless. Then around 300 degrees, you remove that residual binder. You basically burn it. And then because of the thermal expansion, your powder particles, they get into contact because of the high surface energy. When heating further up, they build sintering bridges, and in the end, they build a fully dense microstructure. And it's a procedure that's completely well known for metal injection molding. So basically, the process is like injection molding, metal injection molding, but instead of making your green part with an injection molding machine, you print your green part with this newly developed printer. We sinter in a retort furnace. As said, the debinding and the sintering is a combined procedure, so the parts are not removed in between. We can go up to 1450 degrees here, which means that the most materials could be sintered that way, and the sintering temperature is about 80% of the melt temperature. But that's just a rough rule of thumb. Of course, this has to be optimized to the process and the parts. So you have your 3D data, but because of the removal of this residual binder, you have a shrinkage. And this shrinkage I put down here with roughly 20%. Of course, we know it to the last digit, so 3 digits after the comma. We exactly know the shrinking factor, but this is depending on the material used and the filling ratio. But for each of the feedstock composition, we know the exact shrinking ratio. And because it's a 3-dimensional shrinkage that's the same in all 3 directions. It's very simple. So you blow up your CAD data by the shrinking factor. That in the end you get your final part. So you compensate for that shrinkage. As I said, the parts are very precise. In the finished parts, tolerances of up to 0.5% of nominal dimensions are possible. So we're really in the 1/10 or 100ths range, depending on the dimensions. But you still have a staircase effect due to the layer-by-layer production. That sometimes when people look at the parts, what they forget, but you see it here on this scanned part, it's still kind of staircase approximation of the real geometry. And this can be, especially in jewelry parts, this can be not so nice if you make very large radii, because a very large radius means that you probably have 2 or 3 steps which then are seen as shrinking lines on the surface. So you need a certain kind of strategy to print your parts with very sharp edges, for example, or to do some rework afterwards. The surfaces, as I said, are the best one we currently see in the market. So as sintered means as printed and sintered, we have a surface RA of about 7.5 micron. You see on the right side a profile measurement, what you see. And if you look at it with a very high magnification, you really see the printing pixels. So currently we are using a 4K projector, but we're now going to higher resolutions. So this will get better over time. If you sandblast the material, you can go down to 2.8 micrometers. And if you tumble polish, you can get RAs of 0.03 or RZ of 1.5. All the parts that I show now are not polished by hand. It's all done in machine processes. And again, as we don't have any support structures, that the afterwork really and the rework can be minimized very much. So here's some parts. What you see on the left side, that's the watch case, and this watch case is as printed. So you see here the printing lines on the surface, but this designer, he said he wants to have this special appearance just to feature the printing process. On the right side, you see a flat part. This has a golden appearance, and that's because it's electroplated. So that's a stainless steel part. So we cheated here a bit. Yeah, and you see here on the surface, this is not treated at all. You see the kind of pixel structures. In this watch, the indicators here are also printed 3D, and you see that you even can, this is one centimeter here just for, to give you an idea of the size, how small these parts are. You see the printing lines, yes, but you also can read what you see on the surface of it. On the right side, you see a ring, as printed, only tumble polished. Here, this part looks very interesting, very nice if you have a first look on it, but the thing is a reject part, and I chose it for two reasons. Because you see, first of all, that very delicate structures can be printed. And secondly, you see that this part has not been cleaned properly. So here with the ultrasonic bath, we didn't get out all the not exposed printing material. And if you don't do that, it will sinter together with the rest. So this should have been cleaned better, and this could have been done with a kind of airbrush gun with a very mild spray of material. So the second part that was made was cleaned here much better. Again, you see some printing lines, and this is because the whole thing has an oval shape, a very large radius over it. So this has to be after treated with some hand polishing. As I said, I'm showing pictures here not that have been treated afterwards. So on the right side, a little gimmick here for a trade exhibition. These are some structures just to show what is possible with the process. Here, printed parts, sinter parts on the right side. For scale, you always see either the matchstick or here, this is 1 centimeter. So you see a very, very detailed process, which gives you fine structures. And yeah, the disappointing thing is that the pictures look much worse than the real parts, because the resolution of the cameras is better than your eye. So I would really have liked to come there and have a box of these materials with me to give you a real representation. You can make fully functional part, though this ring with this chain here was printed in one bit, and after sintering the parts, they will stick together a bit. But they are not sintered together, so with a little bit of mechanical pressing and pushing, you can make it fully operable, that you have then a stainless steel chain that has really no connections, and nice gimmick. This watch case you've seen before, and again you see that a very, very high detailed resolution is possible. You see the matchstick here for comparison. Here on the left side, a representation of this ball, which has inner structures. And because of the shrinkage of the material, one can also imagine that it could work together with some inlays that one puts in. The restriction obviously is here that it has to go through the sintering furnace. So if you put in, for example, a precious stone, it has to be temperature resistant to the sintering. On the left side, part only tumble polished. So you see that the surface is really very good and also allows glossy structures. If it would be hand polished, even more. And then on nearly the final slide, this brooch we've made for the Jewellery Museum of Pforzheim. It's actually a copy of an existing part. So what we've done with a scanning machine, with a gum scan, we took the geometry, we printed the part. Then it was electroplated with gold, and then it was hand painted with some cold animal paint. On the right side, always the same part. Here, on the left side, electroplated with gold. All the others are PVD coated in different colors. And just for a comparison, a DMLS part that has been reworked for 3 hours. And you see here where the support structures have been to support the material. On the right side, the same watch case as printed and fitted into the watch case. Because we think that this process is very interesting for industry, and not only for the jewelry industry, but as Dr. Klotz said before, and Dr. Bulling also for medical purposes, for aerospace and so on. We made a spin-off at the university in April 2019, which is funded by the Young Innovators Program of the Ministry of Science, Research and Arts in Baden-Württemberg. And this spin-off is specialized in this LMM procedure and related development. So what they're doing, they're conducting feasibility studies for components and materials, which means you could come to them if you have a design idea, and they would make you 1 or 2 or 5 parts to see if it's feasible, if the geometry is suitable for LMM. They also make small-scale production, so a couple of 100 parts per year, or also a couple of 1,000 parts in some cases are possible. And if your business, your ideas would explode, which would need higher quantities, they are also installing the whole process chain for in-house production. And the process chain means the printer, plus the cleaning devices, plus the sintering furnace, including the parameters that a production can be set up in-house. So that would bring me to the last slide, and I was really talking here in the off. I have no idea if you heard me. I have no idea if you've seen my slides. I hope you did so. And if you have questions, here's my address. I'm happy to answer your question at any time if you come back to me. Thank you very much.
Bene, siamo arrivati alla conclusione della sessione mattutina.
So we've come to the end of the morning session. I don't know if there are questions. Okay. So we break for 3/4 of an hour, and we reconvene at 2. Thank you.
Grazie per essere qui con noi anche nella sessione pomeridiana di JTF.
Thank you very much for being with us in the JTF afternoon session. My name is Friso. I will be the moderator. We'll continue with the presentations of 3D technologies. We have a professor from Thailand, Bungrat Longwatana, who will speak about titanium and precious metal jewelry using the 3D printing technology. He got a PhD in material research at the California Institute of Technology, and at present he is the director of the Research Center of Biomedical Engineering at the Chulalongkorn University. He is the author of many scientific works on biomedical engineering. He has been one of the speakers of the Santa Fe Symposium, his first time at the JTF. He will speak about the different aspects to be considered to be successful with 3D printing, choice of raw material, printing process, shape of the object, and other metallurgy principles which come from the background of metallurgy. Welcome, Professor. You have the floor.
Hello, good afternoon, and greetings from Thailand. Sawadee krap. My name is Bunrat, and thank you for kind introduction. I heard some keywords. I apologize that this presentation is in English language. And I'm really thankful to the organizing committee of JTF. Today I'll be talking about titanium and precious metal jewelry using 3D printing. I'm affiliated at the Chulalongkorn University at the Faculty of Engineering, but I'm also talking on behalf of my spin-off company, Metically, which the majority of the knowledge has been derived from. So quickly about myself, I have been working on material science, and these are some of the work that are related to jewelry manufacturing. For example, in 2007, we worked on a project of 850 platinum alloy that could be processed like plastics. And below are the pellets that were formed and thermoformed at only 270 degrees Celsius. Or in 2016, we did the characterization of gypsum bonded investment materials. And the goal is to do the cycle for burnout within 2 hours. So this is the knowledge that we have to obtain through materials characterization before the program for burnout is accomplished. And as I mentioned, Metically is a company that does 3D printing titanium and polymers. And owing to some of the knowledge that we obtained from this company, I'm sharing with you some of the results and the findings that we have accomplished at the company. And since the product is US FDA approved for the cranioplasty, the skull plate, the geometry, the reliability and reproducibility of 3D printing of titanium is actually very important to accomplish. And these are some of the examples of the products that were 3D printed using titanium. But of course, today we're talking about jewelry and something interesting and nice. So we do printings of other objects as well, like the dragon here. As you see below, the keys are actually within the supports themselves. As you see, it's a typical 3D printed parts, rough surface, but there are some fine details that could be accomplished if the processing parameters are correct. We also make some jewelry pieces, particularly for this event and also for the Santa Fe Symposium later in the year. And some of the rings that are dynamic. These are actually two rings that are interlocked forever, and they're actually movable. All the products on the right-hand side has been polished, and you would see some of the finishing process afterwards. Today, I will be covering about the key considerations during the 3D printing of titanium and other metals via powder bed laser melting. We have 3 machines, and we run several materials in our company and in the laboratory at the university. First is the fundamentals. I think this is quite important, but we will conclude them into shorter terms. But the thermodynamics, chemical fluids, and material science are some of the key considerations. For example, the image shown on the left, you would see that the laser comes down. There is a heat source that normally is laser or electron beam. And then you would have several elements down here. The laser comes down, melt, and there's possibility of vaporization and also the melt pool that is down here. So in order to accomplish the right parameters, we usually work on 2 extreme ends of the conditions. First is the borderline conditions. This refers to the conditions that are barely melting the powder at the edge of the heat affected zone. For example, here is this the work on our tantalum. We use only 100 watts laser power and really fast scanning speed of 500 millimeters per second. You would see that there are some unmelted powder here. The other extreme ends is the infill conditions. We use a lot higher power, 250 watts of the laser power at the scanning speed of only 10 millimeters per second. So you would see that with the slow scanning speed and a lot of power, we actually create some pores. And these are actually evidenced by actual experiments and confirmed by the work of the simulations here. This is our collaboration with Professor Shinjo, Professor Pan Visawat, and Professor Roger Reed in the UK and in Japan. The equations, the governing equations, we take into account the viscous terms, gravitations, and interfacial phenomena such as surface tension, Marangoni's flow. If you like wine, you'll see a lot of this in your glasses as well, and the recoil pressure. And then there is a discussion of the laser heat source and the heat loss due to vaporization, conduction, convection, and radiation. The audience is referred to the following publications by our research groups. Now, back to the printing of the objects. We actually have to print a lot of these because, first of all, we want to achieve the similar strength as the rod products or the investment cast products. And there are also concerns about residual stress management. This is a very big problem in additive manufacturing because of the rapid heating and the subsequent cooling of the solid forms. In our work, we were able to accomplish the as-built strength beyond the standards, and also even with annealing and with the microstructure treatments, we could actually still be above the standards for our printed parts. And this is how we do it. We link the knowledge of phase diagrams, phase transformations, physical metallurgy here on the left-hand side. Above, we are looking at the atoms. As we move from nanoscale to microscales, we have precipitates, textures, and then phases. And eventually we have some cracks and surface roughness. And these are all well explained by many theories in physical metallurgy. The photos on the right-hand side, these are some of the microstructures that have been tailored with the subsequent heat treatment profile to reduce the residual stress and also to change the phases of our titanium, of our silver and copper, of our gold, of our tantalum, for example. Of course, the residual stress, we actually have a lot more failures than success when we started off this project. you would see that each of the cubics here were laser melted at different processing parameters. And you would see that some of these would fracture right in half due to retro stress. So here's a fun question for the audience. This is a question regarding the CTE, coefficient of thermal expansion. We have two cylinders here, left and right. And the left-hand side, the inner diameter is a lot larger. It looks like a shell cylinder. And the right-hand side, it's much smaller diameter. Well, the question is, when we heat up this cylinder, the expansion happens, but would the inside diameters expand or shrink? On the left-hand side, it's actually quite obvious that as the cylinder is heated up, the D1 value, the diameter would expand because the material expands right around here. But for D2, there are two things at play here. The outer circle would definitely expand, but the inner circle, the expansion itself could be towards D2. So this is a sort of the fun experiments that we have to do in order to be able to manage the thermal expansion and the restore stress. So I'd like to share with you some of the test parts that we have for several print parameters. We test print the cylinder or shape like this, and also some bone shapes. If we inspect closely, there are 5 different holes here, cylindrical holes, and also just a vertical slabs here. And the vertical slabs are actually very difficult to accomplish, to have 99.5% density or more. So we do a lot of measurements on the inside and on the outside. After the printing, we actually see that there are a lot of shrinkages and there are some changes in geometry. And I'd like to share with you, this is one really powerful sample to use. And I'll be happy to share the geometry of this, the drawing of this piece after the talk. The geometrical change, we also use laser interferometer to check the change in the height and the curvatures. And as you see here, the scans were performed on the head of this is the elbow joint. We perform on the head of the elbow joint and also on the stem side. So you could see that there is a little bit of variation on the stem side and here in the order of tens of microns that we still have to fix. So these are the main 3 processing parameters that any company should be careful, should be worrying about. First is the incoming raw materials. In this talk, I have actually mentioned about 2 types of powder. First is the elemental powder. This is the powder that has been mixed between at least 2, 3, 4, or 5 elements. You could actually mix them and do the 3D printing right away, but this is quite challenging, but it saves the time if you don't want to make the powder. Another technique is to pre-alloy. This is actually becoming a lot more economical at the moment. There are quite a few lab-scaled or small batch production atomizer. The machines that are available, I think some are also at the fair today. You could do the pre-alloy as well in different quantities. The mix, time, motion, and agitation, and we also look at how flowing the powders are, argon atmosphere, vacuum, or open atmosphere. The SLM printing itself, there are quite a few other parameters that have not been mentioned. For example, the print scan strategy. Scan refers to how you move the lasers around. And then there is the other technique like skin core, skin remelt and core. These are some of the techniques that we employ in different shapes and forms of the parts that we make. The blades refers to the blades that move and lever the powder from left to right. There are several types of blades, rubber, stainless steel, and many other kinds. And the supports, actually, there are 3 main usage of the supports. First is actually for the heat transfer. We use a lot of supports for the thick parts, and also the supports, even though we could use a lot, we actually prefer to use little because of the ease of removal and post-processing. So number one and number two are actually fighting each other. If we want really high quality print, we have to spend a lot more time printing, and that's also cost, and also the problem subsequent of removal process that would take longer time. And of course, the last one is the residual stress and accuracy, and this is the combination of both. The post-processing, we do heat treatments in the range of 700 to 1100 degrees Celsius with covering gas like argon atmosphere. We do also the effect of remelting parameters in the laser itself during the 3D printing. And this could accomplish several mechanical properties of the materials, for example, ductile titanium. And we could also show this result by tensile test. We do a lot of microstructural analysis, and this is also serve as a way to understand which post-processing technique is best for our samples. So the basic printing parameters you would see here, so that we understand the same terminologies here. The laser beam comes down. P is usually referred as power, and sometimes we call it in watts. It's the joules per time or joules per second, that is watts. And then there's a lens, and the lens that comes down here, it's kind of focal points here. And then there is the focal offset distance. This is how, the effective length for the laser to come down and melt properly. The scan velocity is the movement of the laser. And here we have the powder bed temperature as well. As we build more and more piece, as we build up the height in Z level, the powder bed actually becomes heated more and more. Here we also have hatch spacing. That's the distance between each of the scan. And then there's a layer thickness. This is the thickness of the powder that has been poured over. And this is the movement of the stage that lowers down. Usually we do this in maybe 25, 40, 50 microns. So all of these is the energy consideration here. So we calculate the volume energy density, and it is E, and that's joules per cubic meters. And it's calculated easily as the power divided by the scanning speed, the hatch spacing, and the layer thickness. Actually, this is how you create the volume during the scan. So we do a lot of experiments like this. The layer thickness themselves, the patterns, these show only two patterns here. I will cover the scan strategies later, but we have the island and continuous scan at different speeds. You would see that there are different degrees of porosities here. And we are trying to accomplish at this point of a fully dense sample. For the scan strategies, we got this really wonderful review paper by Hao-Liu Jia et al. And they actually performed several scan strategies. For example, unidirectional scan, contour scan, helix scans. And we actually tried quite a few of them. You would see here on the right-hand side, each of the cubics here were actually scanned using different scan strategies. And with the scan strategies, I think we found the island scans to be working quite well, and also double pass of the laser beam as well. This is also helps in the sense of the residual stress. But as you see, when the energy is too high, there are some holes, there's some pores, and when energy is low enough, there is a more dense sample. But you would see some of these dots down here are unmelted powder actually. So there's always the arts to balance all of these scan strategies to work properly. And here, there are some more examples of the you see here 40 plus 50. These are a double pass of the laser beam, and we found this technique to be working the best actually. So we must conclude though that each different materials and alloys have their own optimum parameters, and they have scan strategies for different applications. For us, the double pass is actually working the best. However, this means double the time for the build platform. So depending on the customers, depending on the implants that we make, depending on the jewelry pieces that we make, we actually alter some of these scan strategies so that the results would be most fitted. Surface finishing, we treat these samples just like jewelry materials. You see the tail of the dragon here. This is the as-built roughness, and we have rough grinding and fine grinding, and also polishing techniques. These are all quite straightforward. Actually, we didn't try anything new except the fact that these are all dry process. Titanium doesn't like water. This could be a lot of interest in some of the audience as well. We do a lot of the surface coloring to the oxide layers, and this is called anodizing. And the color could be selectively filtering specific wavelength with respect to the thickness of the oxide layer. This is a refraction process, but the colors are actually very unique. And some of the colors here, you would see it's ranging from yellow, orange, purple, pretty much the rainbow color all the way to green. And we were able to pinpoint the liquids, the chemicals, and also the time and the thickness of the oxide layer so that we could accomplish a color plates like this. And on the finished products, we could do the treatments and also possibility of making double color or multiple colors on just one simple piece. I'd like to end my presentation here, and thank you very much. I believe your imagination is in your hands, and as engineers, we're just here to do the printing and support you. Thank you very much, and I'd like to acknowledge two subsidiaries of ours, particularly the implant company, and Manufact TI is the 3D printing company, 3D printing as a service. Thank you very much for your time and your kind attention. ขอบคุณครับ Grazie.
Thank you very much, Bunrat, for your presentation. And torniamo in italiano adesso.
So now let's go back to Italian. Now we have Marco Giuseppe Andretta. Process parameters developed for different applications and relevance of open material system for jewelry additive manufacturing. Marco is graduated at Politecnico di Milano, and he has been dealing with 3D printing since 2006. He is a product marketing analyst at SISMA with a special focus on additive manufacturing in industrial sectors. The SISMA experience is that in order to have successful projects, we need a combination of skills of raw materials producers and application experts in order to have a systemic collaboration able to meet the requirements of customers. We need parameters, production strategies, and customized materials to meet the need of single customers. Marco, the floor to you.
Farò in inglese.
Come preferisci.
Il telecomando.
Questo è per girare le slide.
Questo qua.
Adesso sì.
Hello everyone, it's a pleasure to be here, and well, I will do this presentation in English just for the sake of also and the benefit of all the people that are following us from abroad. And I will I'm very happy to do this presentation after Professor Lowan Watana, because I feel it's really a continuation of what is doing. Just few words about Sysma. Sysma, it's a company that was founded more than 60 years ago. It started as a company that built micro-mechanics for textile machines, and the first production plant was built in 1967. In 1976, that marked the beginning of the jewelry machines production. So since 1976, we are building machines for chain making. Over the years, the company expanded, and since 2001, we are using and integrating and building laser sources. And following this laser knowledge, we started working with 3D printing machines. We started building 3D printing machines in 2014, and we did this also with a joint venture with a German manufacturer, Trumpf. The company expanded over the years, and we built several new plants, and now we have our own headquarters in Piovene Rocchette. So just to sum up, the company has more than 40 years of experience in jewelry making machines, more than 20 years in laser manufacturing and laser-based process, and more than 10 years in manufacturing of metal 3D printing machines. So the first decision that we made when we started building 3D printing machine was that we wanted to have an open platform, an open system that could give freedom of choice and to our customers, and also to experiment with the parameters. The possibility to adapt building parameters, we think it's crucial for having good success projects, especially in the jewelry making manufacturing. So this is how we see the jewelry making, additive manufacturing for jewelry making. We start from the powder competence. We partner with powder manufacturers that can produce fine spherical powders for laser metal fusion. We know that for jewelry making, it's important to have a robust system, but also a system that can reduce material waste. Precious metals are getting more and more important. And then we have the process qualification. We develop laser and process parameters. All this harmonized approach may give parameters for building high-quality parts with a very high density. We call it digital microstructure, so very fine microstructure that can comply with the jewelry high-quality standards. And also, we develop the parameters in order to have, in order to be adapted to the post-processing. But this is a systemic competence that only gives a metallographic competence. We understand that what's needed is to have a partnership with application specialists that can fine-tune the parameters on the actual jewelry geometries, and then can finally deliver robust and predictable process for the end user. The benefit of having an open system, of course, is the fact that we can have different, really a lot of different alloys, and the list is growing. Now, I will start with the actual presentation. of course, we partner with application and competence centers in all areas of the world that can really transform the parameters and additive manufacturing in final products. So when we talk about building parameters, of course there's base parameters. So regarding laser, we have obviously laser power, scanning speed. Then there's hatching distance. We talked about this before. So the distance between all the laser paths. There's layer thickness, so the thickness of each layer that is being built, and then there's gas speed. But we focus on really a lot more advanced parameters, and we like to give our customers all the freedom to really fine-tune the process. So, for instance, when we talk about laser, there's, of course, laser power and scanning speed, but hatching, it's not just going back and forth with the laser, but it's also the ability to have different hatching strategies, different orders in the hatching, and also contours. Contours they make basically what's the external quality of the surface is like, and being able to vary all the parameters in the contours as well, it's really important. Beam spot, we never talked about beam spot size today. So we think it's important to choose the right beam spot for the right application. Whether the customer wants high quality, small geometries, or is more geared towards manufacturing. Layer thickness, of course, the customer needs to be free of choosing the layer thickness, but also different protective gas. An open system might give the customer the possibility to choose different grain size, different from what standard grain size distribution is. And then, of course, all the parameters, all the laser and hatching and contour parameters are also present in the up skin and down skin. So all the areas that are on the bottom or on the top of the part. So the advanced parameters are not only what happens inside the machine, but we like to think about all that happens before. So when the customer designs a part or orient a part for additive manufacturing or design the supports, and all these parameters needs to be adapted to the actual post-production that has been chosen. So no parameters, there's not a perfect parameters, there's only a perfect parameter for the actual workflow. So just to give you an example, this is basically two examples of two rings. So similar object, but different geometries. Same material, but one has a really small cross section, and the other one is a massive component. You cannot use the same building parameters for these two objects. So a small part might have different validation criteria, so the surface quality needs to be as good as possible as built. There's thin wall section. So when we talk about advanced parameters, of course, we will take in account maybe the beam spot size. We will try to choose a machine with a small beam spot size diameter. Material, grain size distribution might be fine-tuned for the actual project, and the supports, as we discussed before, they will only need to have a supporting function. they're not anchoring the part. There's no need for heat management by the supports, and that's completely different when you're looking at the same object, so a ring, but a massive part. So in this part, the wall thickness changes along the geometry, and maybe the validation criteria changes. Build speed becomes more important. Maybe the actual value of this part, it's in massive production. So when we look at a part like this, it's still a ring, but we will choose a bigger beam spot size. The supports have a completely different value because they are managing heat exchange, and they are not only supporting the part, but also anchoring the part to the platform. And there could be some benefits from preheating to manage internal stresses, and adaptation of skin and core parameters, so different parameters from the outer surface and the inner surface in order to increase even more the build speed. So we looked at two different examples, two different rings, but they need completely different building parameters. Another example, courtesy of our partner Nuovi Gioielli. This is a textile built basically with metal additive manufacturing. In this technical example, where we see there's no correlation with conventional technologies, so it's something really new, and all the part is completely interlaced. But in this case, parameters, they play a huge role in the being able to have the correct functionality of the part. So the part is not changed in the CAD file, but it's basically modified by the building parameters. So the actual dimension of each square could be changed and fine-tuned with beam compensation parameters. So basically the distance from the actual CAD file to the path of the laser. Now I would like to talk about titanium. It has been really a hot topic today. A lot of the people before me, they talked about titanium, and we think it's interesting because there's first of all a growing trend in jewelry regarding titanium, and it has some obvious benefits. It weighs a quarter of gold, so bigger items could be worn and still be comfortable. It's anti-allergenic, so it's let's say a medical grade material that is used also in jewelry making, also for this reason. For instance, titanium cases can be worn by people that are allergic to nickel. So in watchmaking, titanium could be interesting for this reason. And it could be processed, we saw in the presentation before, with a wide range of anodization, so in order to have really new and bold colors. So we focus on titanium because titanium, it's difficult to machine and process with traditional technologies. In traditional processing of titanium is really costly. Machining is really difficult and could also be dangerous sometimes. For those of you that are working a lot with milling machines, you know that probably titanium, you need to slow down the speed of milling in order to avoid unwanted hardening of the metal. So machining is slow, as we saw today from a presentation before, casting titanium as well is a very difficult task. And why titanium for the 3D printing? Well, titanium, it's not only an interesting material, it's one of the materials that can be printed more easily. So it's one of, I would say, probably the easiest material to print. And it's for different reasons. It's highly self-supporting. It really needs a small amount of supports, which leads to a small amount of post-processing. It has a relatively low elastic modulus, so the distortion during the process are limited. And a wide range of alloys are already developed for other markets. So if we look at all the alloys available, we have, for instance, titanium 6.4 in the grade 23. It's quite hard, so it might be difficult to polish manually, but it's really a benchmark material for all the additive manufacturing industry. We have titanium grade 1 and grade 2, so almost pure titanium. The hardness is lower, and it's really interesting for small shops, small jewelry shops. And then we have titanium 6.4 grade 5, really already widely used in the watchmaking industry, and it might be considered as a benchmark in the watchmaking industry. But for most of this application, the grade 23 might be the best choice. It's basically the similar in terms of chemical composition, but it's more pure in terms of oxygen and contaminant quantity. Then I would like to talk about a new alloy that has been developed by University of Trento. It's an alloy that has optimal biocompatibility. Of course, it's an alloy that might have a lot of interest for medical application. And but it has also optimal corrosion resistance. It's completely without vanadium, so it has optimal biocompatibility, but also can be in contact with the skin without any issues. So the new material that has been developed by University of Trento, you can find the source form for their document here, and we did all the manufacturing of the samples, and we found that this new material has even higher buildability than conventional titanium 6.4, so it needs even less supports, and it's also a material that can be heat treated without using argon and at lower temperatures. So this is a comparison of titanium 6.4 grade 23 and this new alloy. Without heat treatment, we see that elongation is quite impressive. And with heat treatment, with simple heat treatment at only 650 degrees Celsius, it could reach and outperform titanium grade 23 in many ways. So this is an example of what can be done with this new alloy. So. Of course, the first application that comes to our mind was eyewear industry. It's an almost unbreakable material, but we think that the possibility to have new features like flexible designs in the jewelry, additive manufacturing. This could be a really interesting material. So just to wrap up, this is what we do in SYSMA. We focus on the development of new alloys for additive manufacturing. We are fine-tuning existing materials, but focusing on the actual geometry and the actual application. And we are taking care of the whole process. So we understood that finding the right parameters was possible only taking into account powders, the building process, heat treatment, and also the post-processing. So thank you very much for your attention.
Grazie. Grazie Marco.
Thank you, Marco. That was the last presentation about 3D sector, and then we're having sustainability presentations. Marcin Pirsak of ARM. Marcin is director of the European section of the Alliance for Responsible Mining, a non-governmental organization based in Colombia, which pursues sustainable development and inclusive development for small to medium-sized mines. So since 12 years, he has contributed to the growth of ARM. He will speak about the power of the gold industry to generate a positive social and environmental impact in mineral supply chains.
Okay, thank you very much for the invitation. It's been really exciting to see all the amazing developments in the jewelry design and processing. So for me, it was also very new, and especially the products, the beautiful works of arts that are exhibited outside. So I would like to invite you today for the next 20 minutes to step back a little bit and think how the precious metals, gold especially in this case, arrives to your workshops, arrives to your offices, and what happens before, and how it is linked to sustainability of jewelry industry and the choices that are made in terms of sourcing. So we're going to start kind of thinking, you know, what's happening before? Where is my gold coming from? Do I know the place, the conditions where it was extracted or processed? Are the impacts of this positive or negative? And I actually made a bit of an experiment yesterday walking around the fair and asking these questions. And to be honest, there weren't very many answers. So brands do not really know very well, you know, what happens behind and how, what happened to the gold that they are working with. So I guess for the industry that really their primal matter is precious metals, it is a very material and important issue to investigate. And today we're going to look at some options, and I have a preferred options that obviously we'll try to convince you about, but let's see. So obviously gold, well, comes from below the ground, and it can be mined by large, you know, let's call them conventional mining operations, so often multinational companies. And that's kind of, you know, there are a lot of issues to be discussed around that. But then there is a sector that is less known, artisanal and small-scale mining. And you can see, a kind of brief definition of what it is. It's sometimes hard to identify, but the OECD says that that these are mining operations, formal or informal, that use simplified forms of extraction, processing, transporting, and normally they are characterized by low capital input and quite high labor input. And we can see it in these numbers. So we can see that although it's very difficult sometimes because of the nature of this activity to have the actual numbers, but we can see that 10 to 20% of global gold production is done by ASM. And it actually affects a lot of people. 20 million people around the world are doing this activity. And you can see actually in the jewelry, in terms of workforce employed, it's 90% of the gold mining industry as all. So what are the practical implications of this? The practical implication is that 1 kilo of gold can provide livelihood for 20, 40 men or women in local communities for a year. So that's really, in terms of employment generation, it's really, really powerful. And here, just a brief look at where it's happening. We can see that it's really a livelihood strategy that is practiced mostly in the developed world, and that is very significant and important for these places. So just to kind of give you an idea of what we're looking for, because looking at the map of the world, we can also imagine that it's a very diverse activity, and indeed it is. So you can look at small businesses, cooperatives, a bit more organized, but also groups of individual miners, especially women in this case. Depending on the geological conditions, we can look at hard rock primary mining. So primary because you go straight to the vein where the gold is located, and obviously you need to use explosives to blast a hole. And you can see that it's normally the tunnels are made in quite a simple way with the use of simple tools. We also look at tailings, so sometimes old industrial mines that have been abandoned, the communities go there and recover whatever content of gold is still there. And alluvial mining, so secondary, so the erosion, geological processes basically wash the gold away from the primary sources, and then it's being washed by people in riverbeds or alluvial plains. Unfortunately, a lot of these deposits are located in forests, so there's also a problematics related to that. So as you can see, because of the informality and the kind of poverty-related character of this activity, well, we can see that it really has a lot of challenges. So that there are some cases of child labor. The environmental management is problematic, especially with mercury use, and so on and so on. Health and safety, really, unfortunately, there is a high rate of accidents. So what do we do with it? It's a problem, unfortunately, but what we are trying to do is to look at it as an opportunity, because really with support, if you provide help and training to these people, it really becomes the greatest opportunity related to the supply chain that the jewelry sector is involved with, to really make a change, to really make a positive impact with the real people. Wait, we forgot about something. So we said that gold was mined, but obviously, there's some gold already on the ground. So why not recycle them? And that's actually quite an obvious, option for companies, for jewelry companies. But unfortunately, especially jewelry companies that already have processes, that permit them to separate the gold from alloys and so on. However, there are some important weaknesses of this strategy. So first of all, you don't really know, where it comes from, the conditions, the kind of the previous life of gold is becoming a bit lost in these cycles. And although obviously there are efforts made to ensure that this recycled gold doesn't come from areas that have been affected by conflict and so on, or some really negative mining. Well, unfortunately, there are some risks that this gold is like water. It gets into holes that it resurfaces at some point. And for us, the biggest, let's say, from the kind of sustainability and social perspective point of view, this mining will continue anyway. So it's not that if companies only start using recycled gold, that miners will stop mining. They're going to do it. Unfortunately, the buyers that will be left for them will be, those who really don't care and offer them worse conditions and kind of leave them in this cycle of poverty. So that's obviously, why we think that it's an amazing opportunity in terms of both risk management and CSR for jewelry. Why risk? I think this is an interesting point because 10 years ago, if you looked at the sector at this artisanal mining, well, obviously we have seen that there are a lot of risks. However, the discussions and the dialogue actually evolves now in an argument. Yes, there are risks, but it doesn't mean that you have to disengage, but just the opposite. It's responsible to engage with them and support them in making this transition. If you don't, as we said, this is really part of the imaginary of the sector. Everyone knows that it's happening, even if you don't try not to look at it. So at the end, it goes back like a boomerang and may hit you if you really, try not to look at it. And obviously, from the kind of positive perspective, the biggest positive impact to be made, especially social impact, is in engaging with ASM. So we try to argue that, if you really want to think about the holistic sourcing policy, you should include at least some artisanal gold. Obviously, it's not very realistic sometimes to think that you can include everything, but it's a nice mix, for example, with recycled and the part of ASM. Why? Because you can support women like Marina from Honduras, that thanks to formal mining, before she was unemployed or kind of scavenging, and now she can support her family working in a processing plant. She's been trained, and for the last 3 years she's been, in a formal employment. Another argument is because the regulatory context is quickly evolving. So the movement of due diligence promoted by the OECD more than 10 years ago, a kind of cornerstone of all these debates, is now being actually included in legislation. So we have the EU regulation on conflict minerals that started in 2021, and at the moment there is a proposal of a new directive on corporate sustainability for the EU, for the due diligence, sustainability due diligence. So this is something that's, that's also, because of legal obligations, it's hard to ignore. Finally, we can have a look also at some of the voluntary industry initiatives that have appeared. And I think for the jewelry, well, especially the RJC, the Responsible Jewelry Council, or maybe LBMA, are quite relevant. And I've seen actually going around the fair some presence, especially of RJC. So why am I here? Because I work for Alliance for Responsible Mining. We are an NGO, and in the introduction we learned that it's based in Colombia, but we've already worked with more than 150 small mines in 24 countries. And how we work? we develop standards. So obviously you don't want to have the same standard, for a small family mine as for the huge corporate mining. So we develop standards that actually are fit for purpose and are possible for these people to comply with. Then we work with the miners to empower them to really comply with these standards and become more stable, more profitable organizations. We try to connect their gold with the markets, mostly jewelry markets, and also obviously for all of this to happen, that there are a lot of things necessary in terms of policies, legislation in the producing countries, and that's also something that we try to promote. So just to kind of give you an idea, obviously I don't want to get into too much detail, but I think it's important to understand that even for these small businesses, there are several things that at the same time that they have to comply with. So they need to get organized first, understand if their mining business actually makes sense from the kind of economical point of view, mining, health and safety, environmental management. Then they have to process the gold in an environmentally friendly and efficient way, and finally sell it, hopefully export, and so on. So it seems that you can maybe make a comparison with a farmer. So you have these big farming companies and a small family farm. So a lot of these things can be a bit difficult to grasp for them. But I would like to show you just a few examples of kind of real life situations where you could really change people's lives. So this is, for example, a process with a mine in Colombia, a very nice mine. It's a family mine. They, apart from mining, they also grow cocoa and keep bees. So there's honey, chocolate, and gold. And with them, we've gone through a process of eliminating mercury, in the process improving the productivity by 42%, and also we're going to hear about water treatment. So also for these smaller places, it's an important part of their environmental responsibility. We also work in Africa, and Burkina Faso. It's a sub-Saharan country in a very dry zone, and actually, mining has caused some deforestation. So they are working to re-establish the forests, and the community is planting trees, is recovering, some of the damages. This is a mine in Honduras, and this is an example of a change in terms of health and safety. So, when they started, it was just kind of a disorganized group of people, and they were doing holes like this. And after a process and investment, we can see a completely different situation. There's a tunnel, proper tunnel with support. They are wearing all the protective equipment, and really also, change the mindset. They're no longer these invaders, but proud small business people, right? And obviously, women are a very important part also in this ecosystem. And here is an example of a kind of additional activity. So these women actually are mineral collectors. So they go through the tailings and try to recycle in a way whatever gold content may have been there. And apart from that, they are starting to work as tailors, making uniforms for the small mine that they are contributing. So some examples, because I think sometimes when you talk about the sector, it can be a bit abstract. So it's good to see people's faces and concrete things that can be achieved. And I think the important message here is that you can actually, if you really try to connect, if you make the effort, you can transform people's lives through responsible artisanal small-scale mining. The question is how? What can we do to do that? So there are different options. I'm going to tell you about the options, the option that we work with. So that's a certification for gold. We mentioned the standards previously, and actually Fairmined. So it's a certification, but it's also recognized as COC, so the chain of custody eligible source by the RJC. I know that's RJC is kind of very popular in the jewelry sector. And you can see that, although it's still the beginnings, there's already a network of almost 400 companies in 33 countries that do their jewelry with Fairmined, that sell it. And in the process, what we do is start with the miners and help them get improved, reach these high-level standards, and also use the premium, so the kind of incentive that makes part of the certification to continue their sustainability journey. And we can see that already, $6 million has been used in this way. Another example of an engagement, that companies or industry bodies can involved with. This is a private-public partnership that is called European Partnership for Responsible Minerals. And it's an interesting initiative. It was funded 4 years ago when the talks about the European regulation for conflict minerals first started. And basically, it was done, it was formed not to repeat the history of the US regulation on the Great Lakes region, where basically people suddenly stopped buying minerals from the Great Lakes region because it started to be a legal risk for them to do so. So obviously, that this, something that maybe was well intended, ended up basically bringing even more poverty for miners because they couldn't then sell their minerals at all. So here we can see 3 pillars. We have the governments. Maybe we can, hopefully Italy can join at some point. For now, it's France, UK, Germany, and the Netherlands. We've got some companies, so private sector, and civil society organizations, NGOs, and so on. So basically what they do is it's an accompanying measure to the regulation, and through kind of this crowdfunding between all these different partners, they fund projects that are really aiming to build these bridges between the artisanal and small-scale mining and the European markets. And finally, I think it's also, there is some help, so it's interesting also for you to have a look. They have a due diligence hub for companies, so there is a due diligence checklist, and it's an interesting resource for companies also to ensure that they are complying with the processes. So that's a bit the message. I think there are a lot of ways to get involved, but I would just like to invite you to have it on your mental map of sourcing. Think that there are some really significant impacts, positive impacts to be had by plugging into this supply chain. And also, from our point of view, we have a lot of success stories from the point of view of marketing, where companies really kind of, build their identity or build their unique selling points on this responsible sourcing. And I think it's easier to connect with people by showing, faces, by showing these histories of transformed lives. So an invitation for you and to spread the word. Thank you very much. Grazie mille per l'invito. Thank you.
We thank you, Marcin, for participating, and torniamo in italiano.
Let's go back to Italian. The next speaker is Filippo Finocchi, who will speak about sustainability, new standards for precious metals. He got a degree at Siena University in financial matters. He had different experiences in refining precious metal, and he is the business development manager since 2020 in Legor Group.
I told you I am the manager for precious metals sourcing, mainly in Legor. So what in my business is really trying to get all the precious metals inside the company. So everything that is connected to this topic is under my profession. So what is important for me is not only bring precious metals inside the company, but is also bring precious metals inside the company that are coming from in certain ways. Certain ways that are really that is important for me to let you understand that are connected to the concept of sustainability, because Legor, you know, that is very very linked to this concept. But what is important for me to understand when I came in Legor was what is sustainability, what is the concept of sustainability, because it's very used, maybe abused in these years. So it was important for me to find a way of thinking to report in Legor in order to find a way to source material in a good way. So the concept of sustainability for precious metal, this is one. Is something that we need to adapt to the precious metals, because sustainability has really a wide range of interpretations. So the first thing that we made has been to define the concept of sustainability, to find when the concept of sustainability originated. And the first time that we, in the history, in the human history, we spoke regarding sustainability has been in this book. In this book is common named has been Our Common Future, the Brundtland Report, in which has been defined what is sustainability for the first time. And the sustainability is the condition of a development capable of ensuring the satisfaction of the needs of the current generation without compromising the possibility of development and of the future generations to realize their own. So this is very important because it's a way of thinking, is a totally changed way of thinking, because now we understand that what we are doing now don't have impact on the next generations. So what we do now have to be done with the concept that we don't have to impact on next generations. So how can we import this concept into precious metals? So first of all, we define what are the precious metals that we are talking about. The first precious metals are the magic 5 precious metals that we are using in the precious metal chain are mainly gold, silver, platinum, palladium, and rhodium. Yes, we also have iridium, we have ruthenium, but we can say that are different metals because they are very tough to find them from recycling sources and are very not used as these 5 metals. So we will concentrate our attention on these 5 precious metals. On making these, we have to look at the figures that are connected to these precious metals, because we are used to speak regarding recycling, regarding mining, but what are the real figures behind these metals? You can see that if we take in consideration, for example, gold, the percentage of the recycled gold in the market is only the 24% of the global supply of the metal. You can see here the last figures, so they are very updated. And the jewelry consumption, I don't know why we don't see the figure, but it's almost the 46% of the consumption. So for gold, we will see later that is different between it is different from in relation to the other precious metals, and we will see why. And it will be connected to the what our colleague Pirsak said before. For what concerns silver, approximately is the same. It's 20% of the total supply is originated by the recycled material. For platinum is the 24%. For palladium is the 35%. For rhodium is the 34%. So we have a big part of the supply in the market that is composed by the recycled material. So when we face these figures, we made the second reasoning. That is why we don't use recycled material to produce jewelry. As I will say something that is maybe is not the right place, but is my opinion. We have in the world the primary needs. Okay, as primary needs, we can understand that are, for example, the needs necessary to survive. Okay, for example, drink, to eat something, to have where to don't feel cold. So these are the primary needs. Then we have the secondary needs. Okay, the secondary needs we can understand. For example, we can consider to read a book. Okay, can be a secondary need. We can go to the cinema. But when we speak regarding the luxury market, maybe it's something that we consider we can consider unnecessary. Okay, but we know that is necessary for our living because it's something that we use for affirmation of our personality in the market. So it's something that we need to manage. Okay. But how can we transform something that is unnecessary in a sustainable product? Okay, using this material, so using recycled material, because you know that we can source material from three main sources. Okay, we have mining, we have refining, we have grandfathered. Grandfathered is something that we don't face usually because it's something that is considered the old gold, for example, the large bars that are in the central banks from the Third Reich, for example. Okay, so the three main sources of material are these three, okay? And if you take in consideration the mine sources, we have open pit mine, we have underground mine, and artisanal mine. Just to let you understand the difference between these three kind of sources, main kind of sources, we have this one, that is the open pit, okay, an open pit mine. You can see the impact in the environment. Then we have the underground mines that are created underground, as the word suggests. And they are creating caves, enormous caves inside underground. And then we have the third one, it is the worst one, you can say, the artisanal mine, in which there are millions of miners that are working in critical conditions. Okay, so when we are speaking regarding the mining sources, obviously the concept of sustainability is something that we cannot apply. Only in the case for the artisanal miners that are certified, okay? Because there are some mines that are certified that we can consider sustainable. But the concept of mining is not sustainable at all, okay? Because we are impacting in the environment. You can consider that now the big mines, when they are open a project, they have to present a feasibility plan. In the feasibility plan, they have to provide also the restoring on the environment. So when you see the final output of the mine after the processing, after the production, you can see the same land, the same seaside, the countryside that you see before. But inside the ground, there are all the wastes that cannot remove from them. So it's not sustainable at all, okay? So when we face this one, we decide to define the sustainable way to make precious metals as a recycled one. Because it's the only one that can bring you material that is not impacting the environment, okay? Also the movement of the material, because when you refine 1 kilo gold, you don't have to move anything. When you refine, for example, if you produce one ring from the mining production, you have to move 20 tons of material to produce it. So it's not sustainable. While for recycling, you have almost 100% of return of the material that you move. So also the cost, the impact on the environment to move the material from a recycled source is very low. And for example, you can recover from everything, because you can recover gold from industrial scraps, you can recover from jewelry scraps, you can recover from disinvestments, you can recover from the sales of the banks, and you can recover from electronic scraps. So, but for the industrial, for example, we have the plating scraps. So there is a word behind. All this material is collected, is recycled, and is then refined into finished product, into final material that is pure metal, okay? And if you can summarize all the chain of precious metals, you can see the very beginning that starts, like everything starts from the mine, and then comes in the processing process. The refinery transforms into finished material, so into fine metal, and then comes into the main 5 main channels that are central banks, that are jewelry, industry, and investment. And then starts the process of recycling. The process of recycling of precious metals is almost infinite because, as I told you, we cover the 99.99% of the material if you are able to do it as a refinery. So the process, when it started once with mine, it's very tough to finish in a short time. So we need to recycle and recycle and recycle because it's the circular economy the future in this moment, also for precious metals. And there are some international organizations, major international organizations that already defined what are the guidelines to follow. And the first one is the OECD that defined in the Annex 2 what is the policy, okay, to purchase the material, the minerals from conflict area or high-risk areas. Okay, so they define already the rules to follow to be ethics, we can say, no? And the second one is the Non-FRAC Act. Is something that is very enormous act in which there are all the rules also for the financial institutions. But it is a point in which regulates what is the sourcing of material from, for example, DRC. Okay, so we cannot originate material from certain countries. So these 2 main acts or organizations decided and stated what are the international rules to follow. And the 3 main organizations operating in the market, the jewelry market and the precious metal markets that are the Responsible Jewelry Council, London Bullion Market Association, and London Platinum and Palladium Market, taken these international rules and created their own rules in order to certify their members. Okay, for Responsible Jewelry Council, we have. We will see later, Code of Practices and Chain of Custody. For the London Bullion Market Association and the London Platinum and Palladium Market, they created the Responsible Gold Guidance, Responsible Silver Guidance. All these guidances are following the same rules. There are some little bit differences, but are almost the same. The base is almost the same. And for Responsible Jewelry Council, it is interesting for us to understand what is the process, in our opinion, to follow to have materials sustainable for our products. We have Code of Practices and Chain of Custody. These are 2 different certifications, and they are totally different. The first one defines the rules to consider ethics, to consider the human rights respected. So all the procedures that a company has to follow to be compliant with the OECD regulation, okay? And embraces many fields because you can see that are the human rights, the labor rights, the health and safety environment. And it started with I don't know if you saw the movie, the Blood Diamonds. No? So in order to certify all the chain, all the diamonds, they created a sort of chain, totally. And the final certification the name is Chain of Custody. And this Chain of Custody started to track every single step of the material inside the chain, from the mine to the refinery, to the manufacturers, to the final retailers. And this is a different certification from the first one, because this certification is not on the material in terms of the supplier that originates the material, but is in terms of the chains of the material from the beginning up to the retailers. So what is important to see is in the Responsible Jewellery Council Chain of Custody certification, if you are certified, you have to create a document when you are selling the material that is the transfer document, the name is transfer document, that you pass to the next chain, okay? The next point have to take this document, okay, and it creates the chain that make all the chain continuous. It is very important because the final retailers has the confirmation that the products that originated from the manufacturers is coming from a product that is coming from the refinery that is eligible. Eligible, it means that the material is compliant with the first certification, that is the Code of Practices. So with this intersection, we have the confirmation that the product that is at the end of the retailer has the characteristic to be considered ethics, okay? It is very ethical. It is very important, this one. And you know that the market trend in this moment is moving to a sustainable way. And you can see that in the Paris Agreement, European Green Deal, they are almost included in the law that we have to follow. So it's no more only something that is from an organization, a non-profit organization. It's included in our rules to follow. And also, millennials is the largest portion of the population, is the next leading generation, is very connected to the Sustainable Development Goal. We can see climate change, peace, justice, poverty. So for us, also the war that is currently in Ukraine is something that is totally different to justify, because we grew up in a way in which peace is our standard, okay? So we are very connected to this way of thinking. And for this reason, we need to consider the recycling sources as the main sources to produce jewelry. But there is a difference between gold and the other metals. Because as you can see, the composition of the market in which we have the supply from recycled and the consumption from jewelry, we can see that there is a lot of recycled material that can be used to produce all the jewelry in the market. So we can almost say that all the jewelry in the market for silver, platinum, palladium, and rhodium can be used and sourced from recycled sources, okay? There is only difference in gold, there is a lack of material. So it means that if you want to continue to produce jewelry in a sustainable way, we have to consume all the recycled material in the market, and then a portion of material originated from the mining sources, but have to be mining sources as the one we saw before. So in which there is a complete traceability of the material, okay? Then there is an additional instrument, okay? Because we can use recycled material, but we cannot grant to our customer that we are using only recycled material. But RGC provides us with an extraordinary instrument that is the provenance claim. Okay, the provenance claim is only a document in which we audited from a third party, in which we declare something, okay, that is, for example, for Legor, that all the material used to produce our products is coming from recycled sources. So with this intersection between code of practices, chain of custody, and provenance claim, you are able to declare that all your production is coming from recycled sources. And it is very, very important, because in this way you can conclude, you can close the chain between sustainability and finished product. As you can see here, I reported a saying on Navaco, but it's not real because I tried to find the source. There are many sources. Navaco was the most interesting. But we don't inherit that from our ancestors. We borrow it from our children. That is the same concept that we saw in the book, Our Common Future. So the way that we are making business now is something that will impact in the future of our children. This is for sure. So we need to act now, okay? And using recycled material, we are immediately acting because in this way we are not impacting the environment. This is the first point. This is the conclusion.
Grazie Filippo.
Thank you, Filippo. Last but not least, Mr. Orlando Ballestrino, an engineer who got a degree on chemical engineering in Pisa in 2000. He is now CEO at the Ecoteam Ltd, and in 2008 became in charge of the company optimizing water consumption in surface treatment.
Tornare indietro?
Il tasto rosso.
Rosso? Indietro. Ok, ci siamo. Allora, buonasera a tutti. Allora, un attimo solo.
Good evening, everyone.
Un po' troppo. Sì, perché scorre in automatico.
Ah, lo scorrimento automatico.
Non so.
Ci sia la pausa.
Aspetti un attimo, Sì, grazie. Allora, una piccola introduzione.
Now, a brief introduction. I will speak about a subject which might appear to have nothing to do with jewels and gold. As a matter of fact, it's something we have already heard of in many of the previous presentations. The mines, titanium, the fashion industry, which is different from the gold industry, but still uses precious metals. Mining, we see that a lot of chemicals and water are used. Then the issue of mercury or cyanide, titanium. We heard about washing titanium or anodization. Now, onto the use of precious metals, not only in the jewelry sector, but also in the fashion industry, i.e. using precious metals as a finishing of an object. Why am I here to talk about this subject? I am a member of ECO team. We deal with preparation, maintenance, and treatment plants of waste waters, what is known as plating in simple terms. We do work in chemistry, aluminum, coating, automotive, plating, aircrafts. Part of the engines on aircrafts are made of titanium. Please note that there has been a great change, which is still ongoing, concerning environmental awareness. Everybody is speaking of that, but why is this thing changing? The first law dealing with wastewater treatment is the Merely law dating back to 1976, which was the first in Europe to deal with the issue of waste waters. And sanctions were envisaged, and the concessions and permissions were requested. If you were not compliant, you had to pay fines. Then, Legislative Decree 152 of 2006, which framed the management of waters. In 2019, that appears to have nothing to do with the environment. We had Industry 4.0. Today, we speak about DNSH. What's that? Industry 4.0 and environment. What are the key points? This is an Italian regulation stating that water treatment plants included in Group 2 Annex A of the materials admitted to transition 4.0 or systems for quality and sustainability assurance, with particular reference to filters and treatment of recovery systems for water, air, oil, chemicals, and dust, with signaling systems of the filtering efficacy, and so on. That is a key point. The issue of sustainability is no longer considered as a mandatory constraint, but as an opportunity. Let's move to the Green Deal. The center pillar of New Generation EU is the Recovery and Resilience Facility, which, among other objectives, aims at supporting actions that contribute to implement the Paris Agreement and the UN Sustainable Development Goals in line with the European Green Deal. The objective is zero pollution for an environment free of toxic substances. The DNSH means do not significant harm. That means that the recovery plan action should not cause any significant harm to the environment, and this is a key principle to access funding of the recovery fund. The plans must include actions which contribute 37% of the resources to the ecological transition. This is based on the provisions of the Taxonomy for Sustainable Finance adopted to promote private sector investment in green and sustainable projects and help achieve the goals of the Green Deal. What are these criteria? Climate change mitigation, climate change adaptation, sustainable use and protection of water and marine resources, transition to the circular economy, including waste prevention and recycling, prevention and reduction of air, water, and soil pollution, protection and restoration of biodiversity and health of ecosystems and oceans. Very rapidly on that. Who is affected in our industry? Those who use C24 4.1 precious metals production and treatment and coating of metals, so plating, goldsmith, and those who modify the surface. So we moved from attitude of leveling sanctions to being able to make proposals and to think about the future. And this is a European pillar, zero pollution for an environment free of toxic substances, sustainable use and protection of water resources in line with the legislation. We had Decree 152, prevention and reduction of air, water, and soil pollution. How can we reconcile the two things in our industry? Low impact plant design, use of low toxicity products. Don't use cyanide to recover gold. This is a key pillar. Design efficient systems, reuse and recovery solutions, zero liquid discharge. These are indeed topics that we heard many times today. Let's now talk about designing efficient plants. What's that? We heard about water, which is used in different forms. Any surface treatment process implies washing. So I do something, I wash the item, do something else, I wash it again. For a coating, I might use nickel plating, then copper plating, then gold plating, and in between I do washings. This is the chassis of a car, which is immersed in a pool. The same happens for the plating plants or the washing of the soil in a mine. Rinsing. the design of the washing system is linked to the process. So depending on the process, I indeed organize the rinsing based on the purpose, nickel plating, plating, and so on the number of rinsing and the type of rinsing. It depends on the production surface, more or less water, and the final goal. If it's the final rinsing, it has certain features. It is the final one. It has different features. X0 is the process, might be gold plating, silver plating, nickel plating, degreasing. Then I can dip the item in multiple tanks till the tank N to obtain the washing I wished, so that the item is washed and rinsed, so that it can be subject to the following processes without damages. This is a single rinsing. I put water within tank 1, 2, and 3. And depending on the organization, the summation of rinsings is done by the quantity of water used in the different processes. I might have an equation which you can read. Why are they necessary?
Cosa vuol dire? Vuol dire che io...
Cascade rinsing. I take the water of the latest tank, which is the cleanest, and I use it as a cascade, which is not going from 0 to N. So it's a counterflowing process between the polluter and the type of washing. These are the equations for cascade rinsing.
Perché abbiamo analizzato?
Why two types of washings? There are plenty, not only two. Well, let's see what is the advantage in using one method in the number of washings and the sequence of washings in our process. If I draw a mass which I have to remove from the item, and I want that in the last rinse I am at 1% of pollutants. If I have to use 1,000 liters in one rinse, if I have 2 cascade rinses, I will use 100. If they are 3, I will use 46 liters. If I do 4 in a cascade, I just use 31 liters. So this is the rinsing system, and that gives us an idea how much water I have to use. So with the same objective, depending on the number of washings, I reduce the quantity of water used. On the contrary, if I do 1 rinse, I have 1%. If 2, that will be 10%, and so on. So if I do 4 cascade rinses, the water which I use will be very concentrated. That means less water, but more polluted.
Vediamo un processo un po' più complesso che si collega al discorso che ho fatto precedentemente, perché se ho poca acqua e questa è molto concentrata, devo poi imparare a gestire quest'acqua, che non sarà facile, perché vuol dire che ne ho poca, è molto concentrata, probabilmente sono al di sopra dei miei limiti di scarico, per cui non la posso scaricare. Quindi uno dei sistemi fondamentali che qui viene accennato e che poi affronteremo sarà il sistema di evaporazione, quindi dei sistemi capaci di gestire poca acqua ma molto concentrata. Questo sistema di questa architettura di lavaggio, quindi abbiamo un nostro processo, un primo lavaggio e poi un lavaggio che in questo caso viene gestito con un processo su cui non affronteremo in questa chiacchierata, sono i lavaggi demerizzati a circuito chiuso su scambio ionico. Sostanzialmente il cuore del sistema è il sistema di evaporazione, il quale è capace di gestire poca acqua molto concentrata. Ecco, vediamo l'andamento, diciamo, della quantità di acqua a parità di inquinante. Vediamo l'andamento dell'acqua che io devo gestire attraverso un sistema di evaporazione per ottenere il mio obiettivo. Quindi il primo lavaggio, che è il lavaggio fondamentale, che può essere fatto a sua volta con più lavaggi, è quello che mi determina poi questa curva, che è una curva di ottimizzazione in termini di volume di acqua che deve essere gestita dal famoso evaporatore che affronteremo dopo, che valuteremo dopo. Qui si vede come varia, diciamo, in funzione del tipo di inquinante, quindi se ho 100 grammi di inquinante, in questo caso cloruro di sodio, sale da cucina, 200 grammi e così via, vediamo come varia la curva e la quantità di acqua per avere il mio punto ottimale, il mio punto ottimo di quantità di acqua da gestire con l'evaporatore. Oltre alla gestione della quantità di acqua, di conseguenza verrà una gestione economica della quantità di energia che mi servirà per gestire tutto quanto. Lo scarico liquido zero può utilizzare diverse tecnologie, filosofie di progettazione, ma il punto chiave è l'ultimo anello, che è quasi sempre un sistema di evapoconcentrazione. L'evapoconcentratore è un sistema che permette di concentrare una soluzione diluite eliminando e recuperando l'acqua. Gli utilizzi principali sono il recupero di soluzioni diluite per essere utilizzate come soluzione di processo e la riduzione degli smaltimenti con recupero di acqua. Ad esempio, se io ho una soluzione di nickel o una soluzione d'oro che però ha un titolo troppo basso, io la posso concentrare per essere riutilizzata nel mio processo, oppure per gestire i famosi lavaggi successivi al mio processo di trattamento galvanico o di altra natura, come può essere il lavaggio dei pezzi di titanio. Che cosa sono, quali sono le tecnologie che vengono utilizzate per evaporare l'acqua? Le tecnologie sono la cosiddetta pompa di calore, che è una tecnologia che è molto simile a quella di un condizionatore per produrre aria calda, aria fredda, oppure se ho delle fonti esterne termiche sia di acqua calda che di acqua fredda, quindi utilizzo sistemi di evapoconcentrazione d'acqua calda, oppure la ricompressione meccanica dei vapori, che può essere in varie forme tecnologiche, circolazione naturale, forzata, falling film. Andiamo ai punti fondamentali. Se io faccio bollire l'acqua e non recupero il vapore che c'è, che produco, io userò 640 watt per litro di acqua o per chilo di acqua, è la stessa cosa. Se utilizzo sistemi a pompa di calore, quindi simili a quelli di un condizionatore che abbiamo in casa, questa tecnologia qui, userò 160 watt per litro di acqua. Se invece ho delle fonti esterne gratis, solamente per far girare pompe, motori e quant'altro, i sistemi ad acqua calda utilizzano 80 watt litro, altrimenti il sistema più economico è la ricompressione meccanica dei vapori, che è un sistema relativamente nuovo, che noi produciamo da circa 15 anni e che consuma solamente 50 watt litro. Il motivo per cui sono qui è perché la Legor ha installato un sistema del genere ed è molto contenta. Questo è il motivo. Conclusioni. La riduzione del consumo d'acqua fino al punto estremo dello scarico liquido zero nei processi di trattamento superficiale persegue l'obiettivo di inquinamento zero per un ambiente privo di sostanze tossiche. I costi di esercizio, che sembravano essere folli fino a qualche anno fa si sono ridotti molto con i nuovi sistemi di evapoconcentrazione, per cui possiamo ritenere questi processi molto vantaggiosi. Grazie.
Grazie ingegnere per quest'ultima presentazione. La lista delle memorie da presentare con questa si conclude. Se ci sono domande, faccio la domanda di rito, anche se siamo rimasti in pochi qui. Siamo ancora disponibili.
We are ready, otherwise we can close this 17th edition of JTF and see you again in our social media to visualize the presentations, which will be available shortly. So even though you could not participate, you will have the opportunity to visualize the presentations. On behalf of the organizing committee of JTF, I would like to thank you and see you soon. Bye.